Welcome, fellow dreamer. Tonight, we journey through humanity's timeless fascination with the heavens above, from the earliest stargazers who mapped the night sky to the brave pioneers who first ventured beyond our atmosphere into the infinite cosmos. This story unfolds alongside gentle music and flowing abstract visuals, revealing remarkable moments and hidden wonders from our quest to touch the stars. As you listen, let these tales of discovery quietly nourish your curiosity while guiding you toward peaceful rest. So take a slow, deep breath. Let yourself sink into softness and comfort. Allow your mind to wander among the constellations as your eyes grow heavy, and simply let the story carry you gently into sleep. Long before rockets pierced the sky, before telescopes magnified distant worlds, before equations described the motion of planets, human beings looked upward and wondered. On clear nights, when darkness settled over ancient villages and cities, people gazed at the thousands of points of light scattered across the heavens and asked questions that would echo through millennia. What were these lights? Why did they move in their mysterious patterns? And what did their movements mean for life on Earth? The earliest astronomers possessed no instruments except their eyes, no tools except patience and memory. Yet from these simple beginnings, they built the foundation of knowledge that would eventually carry humanity into space itself. They watched, they recorded, and they began to understand that the sky was not random chaos, but an ordered realm following patterns as regular as the seasons. In ancient Mesopotamia, between the Tigris and Euphrates rivers, the Babylonians developed astronomy into something approaching a science. Around 4,000 years ago, their priests climbed to the tops of ziggurats, stepped pyramids that brought them closer to the heavens, and kept careful watch on the night sky. They noticed that most stars maintained fixed positions relative to one another, rotating overhead like jewels set in an enormous sphere. But they also observed wanderers, stars that drifted through the constellations following their own paths. These wandering stars, which we now call planets, fascinated the Babylonian astronomers. The Babylonians were meticulous record keepers. On clay tablets, they inscribed their observations using wedge-shaped cuneiform script. They tracked the movements of Venus across the sky, noting its appearances as both morning and evening star. They recorded lunar eclipses, solar eclipses, and the positions of planets among the constellations. Over generations, these records accumulated into a vast library of celestial knowledge. The Babylonians discovered that eclipses followed predictable cycles, and they learned to forecast when the moon would darken or the sun would be obscured. This ability to predict the future movements of celestial bodies must have seemed almost magical to their contemporaries. Far to the southwest, along the fertile banks of the Nile River, Egyptian astronomers pursued their own observations. The Egyptians organized their year around the reliable flooding of the Nile, which brought life-giving water and nutrients to their fields. They noticed that the brightest star in the sky, Sirius, reappeared on the eastern horizon just before dawn at the same time each year, shortly before the floods arrived. This heliacal rising of Sirius became a cornerstone of the Egyptian calendar. The Egyptians divided the night sky into 36 groups of stars called decans. As Earth traveled around the Sun, different decans would rise at dusk throughout the year. By watching which decan appeared on the eastern horizon at nightfall, Egyptian astronomers could determine the date with reasonable accuracy. They developed a calendar of 12 months, each containing 30 days, with 5 additional days added at the year's end. This gave them a 365-day year, impressively close to the actual length of Earth's orbit. Egyptian temples were often aligned with astronomical precision. The Great Pyramid of Giza, built around 4,500 years ago, has sides that align almost perfectly with the cardinal directions: north, south, east, and west. The narrow shafts inside the pyramid pointed towards specific stars that held religious significance. The Temple of Karnak features an axis aligned with the winter solstice sunrise. These architectural achievements demonstrate that Egyptian priests possessed sophisticated knowledge of celestial movements and could apply that knowledge to monumental construction projects. Meanwhile, on the opposite side of the world, Chinese astronomers were developing their own rich tradition of sky watching. Chinese records of celestial observations stretch back more than 3,000 years, making them among the oldest continuous astronomical archives in existence. Chinese astronomers served the emperor, and their duties included watching for unusual events in the heavens that might signal changes in earthly affairs. The Chinese kept detailed records of comets, noting their appearances, brightness, and the direction of their tails. They documented novae, which they called guest stars, sudden bright points of light that appeared where no star had been before. One such observation from the year 1054 describes a guest star so brilliant it could be seen in daylight for 23 days. Modern astronomers have identified this as the supernova that created the Crab Nebula, still visible today through telescopes. Chinese astronomers also tracked sunspots, dark patches that occasionally appear on the sun's surface. They observed these during times when dust in the atmosphere dimmed the sun enough to allow direct viewing without damaging their eyes, or by looking at the sun's reflection in water. These sunspot records, spanning 2,000 years, have proven valuable to modern scientists studying the sun's long-term behavior. The Chinese developed their own constellation system, quite different from the patterns recognized by Babylonian and Greek astronomers. They divided the sky into 4 regions, each associated with a mythical animal: the azure dragon of the east, the vermilion bird of the south, the white tiger of the west, and the black tortoise of the north. Within these regions, they identified hundreds of individual constellations, many quite small compared to the sprawling figures familiar in Western astronomy. All these ancient civilizations recognized the practical value of astronomical knowledge. Farmers needed to know when to plant crops and when to harvest. Priests needed to schedule religious festivals at the proper times. Travelers and merchants needed to navigate across deserts and seas, using stars as guideposts. The sky served as both calendar and compass, making astronomy one of humanity's most useful sciences. But beyond practical applications, there was something deeper at work. The night sky stirred the human imagination and provoked profound questions. Ancient observers noticed that despite constant change, the heavens operated according to laws that seemed eternal and unchanging. The sun rose and set. The moon waxed and waned. The stars wheeled overhead in their nightly dance. Eclipses arrived on schedule, This regularity suggested an underlying order to the universe, a cosmic clockwork governed by principles that might be understood. By carefully observing the sky and recording what they saw, these ancient astronomers took the first steps on a journey that would eventually lead humanity into space. They demonstrated that the universe was knowable, that its mysteries could be unraveled through patient observation and logical thought. They created the first star catalogues and sky maps, preserving knowledge that would be passed down through generations. They built the foundation upon which all later astronomy would rest. As centuries passed and civilizations rose and fell, the accumulated wisdom of these ancient sky watchers would flow into new cultures that would take astronomical understanding even further. Scholars would begin not merely to record what they saw, but to ask why the heavens behaved as they did. They would construct models and theories, attempting to explain the mechanisms behind celestial movements. The story of humanity's relationship with the cosmos was about to enter a new phase, one where observation would be joined by theoretical reasoning. As the ancient civilizations turned their gaze toward the heavens and catalogued the movements of celestial bodies, the stage was set for a new kind of inquiry. The meticulous observations of the Babylonians, Egyptians, and Chinese had revealed patterns in the sky, but questions remained. What was the nature of these glowing points of light? How did the cosmos arrange itself? What laws governed the movements of the planets and stars? These questions would find their first systematic answers in the warm waters of the Mediterranean, where Greek philosophers began to contemplate not just what the heavens did, but why they did it. In the bustling cities of ancient Greece, thinkers gathered in academies and porticos to debate the fundamental nature of the universe. They sought to move beyond mere observation toward understanding the underlying structure of reality itself. These philosophers approached the cosmos with reason and logic, constructing elaborate models to explain the celestial phenomena their predecessors had so carefully recorded. Aristotle, who lived in the 4th century before the Common Era, created one of the most influential cosmological models in human history. His universe was orderly and perfectly symmetrical, with Earth positioned at the absolute center. Around our world, he proposed, the moon, sun, planets, and stars were embedded in crystalline spheres that rotated with mathematical precision. Each sphere moved with its own characteristic motion, carrying its celestial body along an eternal, unchanging path. The spheres themselves, Aristotle believed, were composed of ether, a perfect and incorruptible fifth element, entirely different from the earth, water, air, and fire found in the terrestrial realm. This geocentric model, with Earth at the center, seemed to match everyday experience perfectly. The ground beneath our feet feels stable and motionless. The sun appears to rise in the east, arc across the sky, and set in the west. The moon follows its own stately progression through the heavens. Why would anyone doubt that Earth stood still while everything else revolved around it? Aristotle's system provided philosophical reasons for what intuition already suggested, and his towering intellectual authority ensured that his cosmic model would shape thinking for nearly 2,000 years. Yet even in ancient times, not all Greek thinkers agreed with this Earth-centered view. Aristarchus of Samos, who lived about a century after Aristotle, proposed a radical alternative. Perhaps, Aristarchus suggested, the Sun occupied the center of the cosmos, with Earth and the other planets revolving around it. This heliocentric model explained many of the same phenomena, while offering a simpler arrangement. The apparent daily motion of the stars could be explained by Earth rotating on its axis, rather than the entire cosmic sphere spinning around us. The wandering paths of the planets made more sense if Earth itself was moving. Despite its elegance, Aristarchus's sun-centered model found few supporters in the ancient world. The objections seemed overwhelming. If Earth truly hurtled through space, why didn't we feel this motion? Why didn't objects fly off into the void? If Earth moved around the Sun, the nearby stars should appear to shift position relative to more distant stars. Yet no such parallax could be detected with the instruments available to ancient astronomers. To explain the lack of parallax, Aristarchus had to propose that the stars were unimaginably distant, so far away that Earth's motion created no measurable shift. This seemed an extravagant assumption to most philosophers, who preferred the apparent simplicity of a stationary Earth. Centuries later, another Greek thinker refined the geocentric model into its most sophisticated form. Ptolemy, working in Alexandria during the 2nd century of the Common Era, inherited a problem that had troubled astronomers for generations. While the basic geocentric model worked well for the Sun and Moon, the planets presented complications. As viewed from Earth, planets sometimes appeared to slow down, stop, and even move backward in what astronomers called retrograde motion, before resuming their normal path across the sky. How could this strange behavior be reconciled with the perfect circular motions of Aristotle's crystalline spheres? Ptolemy's solution demonstrated remarkable mathematical ingenuity. He proposed that each planet moved along a small circle called an epicycle, while the center of that epicycle moved along a larger circle called a deferent around Earth. By carefully adjusting the sizes and speeds of these circles, Ptolemy could accurately predict planetary positions and account for retrograde motion. He even placed Earth slightly off-center from the deferent center and introduced another point called the equant to maintain uniform angular motion. The resulting system, though complex, worked remarkably well for predicting celestial positions. The Ptolemaic system became the foundation of the Almagest, Ptolemy's astronomical masterwork that would serve as the authoritative text on astronomy for nearly 14 centuries. His model could predict eclipses, planetary conjunctions, and the positions of celestial bodies with impressive accuracy. For practical purposes, it worked. And in an era when practical results mattered greatly for calendar making and astrology, this success ensured the model's longevity. Throughout the medieval period, scholars in the Islamic world and Christian Europe studied, refined, and transmitted Ptolemy's geocentric model. Astronomers added more epicycles and adjustments to improve the system's predictive power. The model became increasingly elaborate, but its fundamental assumption remained unchallenged. Earth stood motionless at the center of creation, while the heavens revolved around us. This Earth-centered cosmos aligned comfortably with philosophical and theological frameworks that placed humanity at the center of divine attention. The arrangement seemed natural, fitting, and proper. The heavens above were perfect and eternal, while the earth below was changeable and temporary. Everything had its proper place in a cosmic hierarchy that stretched from the mundane soil beneath our feet to the most distant celestial spheres. Yet the seeds of change had been planted centuries earlier by Aristarchus. His heliocentric vision, though nearly forgotten, had been preserved in ancient texts. These manuscripts, carefully copied and maintained through generations, waited patiently in libraries and monasteries. When the time was right, when new observations revealed the limitations of the old model, these ancient ideas would be rediscovered and transformed into a revolution that would forever change humanity's understanding of its place in the cosmos. The Greek philosophers had established the questions and created the first systematic models. The debates they initiated between geocentric and heliocentric worldviews would echo through the centuries, eventually leading to discoveries that those ancient thinkers could scarcely have imagined. The old ways of understanding the cosmos, with Earth resting motionless at the center of creation while the heavens wheeled overhead, had held sway for more than 1,000 years. The model seemed to match what anyone could observe simply by watching the sky. The ground beneath our feet felt stable and unmoving, while the sun, moon, planets, and stars appeared to circle above us. Yet as the Renaissance dawned across Europe in the 15th and 16th centuries, a revolution in thinking was quietly beginning, one that would forever transform humanity's place in the universe. In a quiet corner of Poland, a canon of the Catholic Church named Nicolaus Copernicus spent his evenings studying the motions of the planets. Born in 1473 in the town of Torun, Copernicus had studied mathematics, astronomy, and medicine at universities in Poland and Italy. He lived during a time when the tools of observation were still quite limited, yet the desire to understand the cosmos had never been stronger. As he worked through the mathematical calculations that described how the planets moved across the sky, he became increasingly troubled by the complexity of the existing system. The geocentric model, refined over centuries, required elaborate mechanisms to explain what astronomers actually observed. Planets sometimes appeared to slow down, stop, and move backward across the sky before resuming their normal motion, a phenomenon called retrograde motion. To account for this, the old model relied on epicycles, small circles upon which planets moved while simultaneously traveling along larger circles around Earth. Some planets needed epicycles upon epicycles, creating a mathematical framework of considerable intricacy. Copernicus wondered if there might be a simpler explanation. Drawing inspiration from ancient Greek thinkers who had proposed that Earth might move, he began exploring an audacious possibility. What if Earth was not the center of everything? What if, instead, the Sun occupied the central position, and Earth was merely one of several planets orbiting it? As he worked through the mathematics, something remarkable emerged. The retrograde motion of the planet could be explained naturally as an effect of Earth's own motion, combined with the motion of the other planets. When Earth, moving in its orbit, overtook a slower outer planet like Mars, that planet would appear to move backward against the background stars, just as a car you pass on a highway seems to move backward relative to you. The heliocentric model, with the Sun at the center, was mathematically more elegant and required fewer assumptions. Yet Copernicus understood that this idea would be controversial. It contradicted not only centuries of astronomical tradition, but also common sense and everyday experience. He worked on his theory for decades, refining his calculations and preparing a comprehensive manuscript. He shared his ideas in a brief outline that circulated among scholars, but he hesitated to publish his full work. Only at the end of his life did Copernicus finally allow his great book, De Revolutionibus Orbium Coelestium, or On the Revolutions of the Heavenly Spheres, to be published. Legend holds that he received a printed copy on his deathbed in 1543. In this work, he laid out a new vision of the solar system with mathematical precision. The Sun rested at the center, and the planets, including Earth, orbited around it in circular paths. The Moon alone orbited Earth. The stars were distant and fixed in space, no longer attached to a rotating sphere. The book did not immediately overturn the old worldview. Many scholars found the mathematical aspects useful, while remaining skeptical about whether Earth truly moved through space. Others dismissed the idea entirely. Yet the seed had been planted, and a new generation of astronomers would build upon Copernicus's foundation. Among these was Tycho Brahe, born in Denmark in 1546. Tycho was a nobleman with a passion for astronomy and the resources to pursue it on a grand scale. He possessed something equally valuable: an obsessive dedication to precision. In an era before telescopes, Tycho understood that better theories required better data. He set out to observe the heavens with unprecedented accuracy. Tycho's life had its dramatic moments. As a young man, he lost part of his nose in a duel with another nobleman over a mathematical dispute and wore a prosthetic replacement for the rest of his life. But it was his astronomical work that would secure his legacy. The King of Denmark, Frederick II, granted him the island of Heaven and funded the construction of Uraniborg, a magnificent observatory unlike any that had existed before. Here, Tycho installed large, precisely crafted instruments for measuring the positions of stars and planets. Night after night, year after year, Tycho and his assistants measured celestial positions with meticulous care. He could determine the location of a star or planet to within a fraction of a degree, an astonishing achievement for naked-eye astronomy. His observations were systematic and comprehensive, creating the most accurate catalogue of stellar and planetary positions that the world had ever known. Interestingly, despite his dedication to observation, Tycho did not fully embrace the Copernican system. He developed his own compromise model, in which the Sun and Moon orbited Earth, but the other planets orbited the Sun. This geo-heliocentric system preserved Earth's central position, while adopting some features of Copernicus's model. It was mathematically equivalent to the Copernican system for many purposes, but maintained the comforting notion that Earth remained special and stationary. Tycho's treasure trove of precise observations would prove more important than his own theoretical preferences. Toward the end of his life, he moved to Prague and took on a young assistant, a brilliant mathematician named Johannes Kepler. When Tycho died in 1601 Kepler inherited access to decades of the most accurate astronomical data ever collected. This data would prove instrumental in unlocking the true nature of planetary motion, though that discovery would come with struggles of its own. The Renaissance had set in motion a transformation in how humanity understood its home in the cosmos. Copernicus had proposed a bold new architecture for the solar system, one that displaced Earth from its ancient throne at the center of creation. Tycho Brahe had provided the observational foundation that any successful theory would need to explain. The stage was set for the next great leap forward, one that would come from examining Tycho's meticulous measurements through fresh eyes and revealing secrets about how the planets actually moved through the darkness of space. The revolution in astronomy was gathering momentum, and soon it would become impossible to ignore. The early 17th century brought with it a transformation that would forever alter humanity's relationship with the cosmos. While Copernicus had planted the seeds of a new understanding, and Tycho Brahe had gathered precise observations of planetary movements, the universe remained largely a mystery, visible only to the naked eye. The stars were points of light, the planets were wandering luminaries, and the moon's surface was thought to be perfectly smooth, perhaps even crystalline. All of this was about to change through the work of an inquisitive Italian mathematician who would turn a simple device toward the heavens and discover worlds within worlds. Galileo. Galilei had heard rumors of a curious instrument created by Dutch spectacle makers that could make distant objects appear closer. In 1609, working in Padua, he set about improving this design, grinding his own lenses with meticulous care. Where the original devices might magnify objects 3 times, Galileo's refined telescope achieved a magnification of 20 times or more. This was no mere parlor trick or aid for viewing distant ships at sea. Galileo understood immediately that this instrument could pierce the veil that had hidden the true nature of celestial objects since the beginning of human observation. On a clear evening in late 1609, Galileo pointed his telescope at the moon, and what he saw astonished him. The lunar surface was not smooth and perfect as Aristotelian philosophy had long maintained. Instead, Galileo observed mountains casting long shadows, valleys cutting deep into the terrain, and countless craters pockmarking the surface. He made careful drawings and calculations, even estimating the height of lunar mountains by measuring their shadows. The moon, it turned out, was a world much like Earth, with geological features that spoke of a complex history. This single observation challenged the ancient belief that celestial bodies were fundamentally different from our terrestrial home, perfect and unchanging spheres moving through the heavens, according to divine geometry. But the moon was only the beginning. As Galileo continued his nightly observations through the winter of 1609 and into January of 1610, he turned his attention to Jupiter, that bright wanderer that had puzzled astronomers for millennia. On the evening of January the 7th, he noticed 3 small stars arranged in a straight line near the planet. This seemed curious, but not extraordinary at first. The heavens were, after all, filled with stars. Yet when he looked again the following night, these stars had moved. They were now on the opposite side of Jupiter. Night after night, Galileo tracked these mysterious lights and soon discovered a 4th companion. Sometimes they would vanish, passing behind Jupiter or in front of it, Sometimes they would change their arrangement, moving closer together or spreading farther apart. The truth gradually became undeniable. These were not distant stars at all. They were moons, worlds orbiting Jupiter, just as the moon orbited Earth. Here was a miniature solar system, visible proof that not everything in the cosmos revolved around our planet. The Ptolemaic model, which placed Earth at the center of all celestial motion, had insisted that everything must circle our world. Yet Galileo could see with his own eyes that Jupiter commanded the loyalty of at least 4 moons, later to be named Io, Europa, Ganymede, and Callisto. If Jupiter could have its own satellites, then Earth, well, was not unique. The Copernican model, which suggested that Earth was merely one planet among several, gained powerful supporting evidence from these tiny points of light dancing around the giant planet. Galileo published his findings rapidly, eager to share these discoveries with the world. His book, Sidereus Nuncius, or Starry Messenger, appeared in March of 1610 and caused an immediate sensation. The universe had suddenly become more complex, more interesting, and more populated than anyone had imagined. Telescopes were still rare and difficult to construct properly. So many scholars had to take Galileo's word for what he had observed, but those who did manage to replicate his instrument confirmed his findings. The sky was no longer a simple dome of light, but a vast space filled with worlds. As Galileo continued his observations throughout 1610 and beyond, more surprises emerged. Saturn appeared odd through his telescope, bulging on either side, as if it had handles or perhaps companion bodies. His telescope was not powerful enough to resolve these bulges into rings, and the appearance would change over time as Earth's viewing angle shifted, leading to considerable puzzlement. Later, astronomers with better instruments would clarify that Saturn was encircled by a magnificent ring system, but Galileo's observations were the first hint of this extraordinary feature. Perhaps most importantly, for the debate between the Copernican and Ptolemaic systems, Galileo observed Venus over many months and discovered that it displayed phases just like the moon. He watched as Venus progressed from a full disk to a crescent and back again. Under the Ptolemaic model, where Venus was supposed to orbit between Earth and the Sun, Venus should never appear more than partially lit from our perspective. But Galileo observed Venus going through a complete cycle of phases, which could only happen if Venus orbited the Sun, not Earth. This observation was devastating to the geocentric model. The evidence was becoming overwhelming that Copernicus had been correct. Earth and the other planets indeed orbited the Sun. Galileo also turned his telescope toward the Milky Way, that luminous band stretching across the night sky that had inspired countless myths and stories. Through his telescope, this ghostly river of light resolved into countless individual stars, far too numerous and distant to distinguish with the naked eye. The universe was not just larger than previously thought, but vastly more populous, containing multitudes of stars beyond easy comprehension. These discoveries marked a profound shift in human understanding. The telescope had revealed that the universe was not arranged according to ancient assumptions about perfection and hierarchy. Celestial bodies were complex worlds with their own features and systems. Earth was not the center around which everything revolved, but one planet among others, all following the same physical principles. The boundary between the terrestrial and the celestial, so long maintained by philosophical tradition, had begun to dissolve. The same laws that governed falling objects on Earth might also govern the motion of moons around Jupiter and planets around the Sun. As word of Galileo's discoveries spread across Europe, they sparked both wonder and controversy. Some embraced these new insights eagerly, recognizing that humanity's understanding of the cosmos had entered a new era. Others resisted, troubled by implications that seemed to challenge long-held beliefs about Earth's special place in creation. But the observations themselves could not be denied by anyone who looked through a telescope with an open mind. The universe had revealed some of its secrets, and there would be no returning to the simpler cosmos of earlier times. Galileo's telescope had opened a door to new worlds, and humanity had taken its first clear look at the intricate clockwork of the heavens, setting the stage for even deeper investigations into the mathematical principles that govern these celestial motions. As Galileo's revolutionary observations began to spread across Europe, a question remained that would occupy the greatest minds of the 17th century. The evidence now clearly suggested that planets, including Earth, circled the Sun. But why did they move in this way? What invisible force guided these celestial wanderers along their paths? And could mathematics describe the patterns these worlds traced across the heavens? In the early 1600s, a German astronomer named Johannes Kepler inherited something precious. Tycho Brahe, who had spent decades making the most precise observations of planetary positions ever recorded, passed his careful measurements to Kepler before his death in 1601. These observations were remarkably accurate, noting the positions of Mars and other planets night after night, year after year. Kepler devoted himself to finding the mathematical patterns hidden within these numbers. For years, Kepler worked with Tycho's observations of Mars, trying to fit the planet's path to a perfect circle. The ancient Greeks had believed that celestial motions must be circular, the most perfect of shapes. But no matter how Kepler arranged his circles, they never quite matched what Tycho had observed. The differences were small, less than 8 minutes of arc. A measurement so tiny, it would have satisfied earlier astronomers. But Kepler trusted Tycho's precision completely. If the observations didn't fit circular orbits, then perhaps the orbits themselves were not circles. In 1609, after years of calculations, Kepler published his first 2 laws of planetary motion. The first law stated something that contradicted centuries of assumption. Planets, Kepler declared, move in ellipses, not circles. An ellipse is an oval shape, stretched along one direction, with 2 focal points instead of a single center. The Sun, Kepler discovered, sits at one of these focal points. Mars and the other planets trace elliptical paths around our star, sometimes approaching closer, sometimes swinging farther away. His second law described how planets move along these elliptical paths. As a planet orbits the Sun, it speeds up when closer to our star and slows down when farther away. Kepler expressed this with elegant geometry. An imaginary line connecting a planet to the Sun sweeps out equal areas in equal times. When the planet moves through the portion of its orbit nearest the Sun, it must travel faster to sweep the same area as when it glides through the more distant parts of its path. these two laws finally matched what Tycho had observed in the heavens. 10 years later, in 1619, Kepler published his third law, which revealed a beautiful relationship between a planet's distance from the Sun and the time it takes to complete one orbit. Planets farther from the Sun take longer to circle it, but not in a simple proportion. The relationship follows a precise mathematical formula. The square of a planet's orbital period relates to the cube of its average distance from the Sun. This meant that if you knew how far a planet was from the Sun, you could calculate how long its year must be, or vice versa. These three laws transformed astronomy from observation into prediction. Astronomers could now calculate where planets would appear months or years into the future with remarkable accuracy. But while Kepler had described how planets moved, he could not explain why. What caused planets to follow elliptical paths? What force made them speed up and slow down? The answer to these questions would come from England, from a mind that would unite the heavens and earth under a single set of mathematical principles. Isaac Newton, born in 1642, the same year Galileo died, possessed an extraordinary gift for mathematics and natural philosophy. In the 1660s, while still a young man, Newton began thinking deeply about motion and force. The story is often told that an apple falling from a tree inspired his thoughts about gravity, and while the details may be embellished, the essence holds truth. Newton wondered if the same force that pulled an apple downward might extend far beyond Earth's surface, perhaps even reaching the moon. Newton imagined the moon as a projectile, like a cannonball fired horizontally from a mountaintop. If fired slowly, the cannonball falls to Earth nearby. If fired faster, it travels farther before landing. But if fired fast enough, the cannonball would fall at the same rate Earth's surface curves away beneath it. The projectile would never hit the ground. Instead, falling around Earth in a continuous orbit. Perhaps the moon, Newton reasoned, was perpetually falling toward Earth, but moving sideways fast enough to keep missing it. Working through the mathematics, Newton discovered that gravity must diminish with distance following a precise formula. The attractive force between two objects decreases with the square of the distance separating them. If you double the distance between two masses, the gravitational force between them becomes 1/4 as strong. If you triple the distance, the force drops to 1/9. This inverse square law, as it became known, made specific predictions about how objects should move under gravity's influence. Newton then proved something remarkable. Using calculus, a new form of mathematics he developed for this very purpose, he showed that his law of universal gravitation perfectly explained Kepler's three laws of planetary motion: the elliptical orbits, the changes in speed, the relationship between distance and period, all emerged naturally from Newton's simple formula describing gravitational attraction. The same force that pulled apples downward also held the moon in orbit and guided planets around the sun. In 1687, Newton published his masterwork, the Principia Mathematica, often called simply the Principia. Written in Latin and filled with geometric proofs, this book presented his three laws of motion and his law of universal gravitation. Every object attracts every other object with a force proportional to their masses, and inversely proportional to the square of the distance between them. This single principle explained falling objects on Earth, the Moon's orbit, the paths of planets, the movements of comets, and even the tides raised in Earth's oceans by the Moon's gravitational pull. Newton's laws gave humanity predictive power over the cosmos. Astronomers could now calculate planetary positions centuries into the future or reconstruct their locations in the distant past. When comets appeared, astronomers could determine their orbits and predict their return. The clockwork of the heavens operated according to mathematical principles that human minds could comprehend and apply. These achievements by Kepler and Newton laid the foundation for everything that would follow in space exploration. Without understanding that planets follow elliptical orbits according to gravitational laws, humanity could never have planned trajectories to carry spacecraft beyond Earth. Every satellite launched into orbit, every probe sent to another planet, every mission to the Moon follows the principles these men discovered. The mathematics they developed centuries ago remains the language we use to navigate the solar system, to calculate launch windows, and to predict where distant worlds will be when our spacecraft finally arrive after journeys lasting years. As the 18th century dawned, astronomers possessed both the telescope to observe the heavens and the mathematics to understand what they saw. The stage was set for a new phase of discovery, one that would reveal just how vast the Sun's family of worlds truly was. With Newton's laws of gravity firmly established as the mathematical language of the cosmos, astronomers across Europe turned their telescopes skyward with renewed purpose. The solar system that had been known since ancient times consisted of just 6 planets: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Beyond Saturn lay what most believed to be the realm of fixed stars, unchanging and eternal. Yet the universe was about to reveal that it held more secrets than anyone had imagined. On a cool March evening in 1781, William Herschel was conducting one of his routine surveys of the night sky from his home in Bath, England. A musician by profession, Herschel had developed a passionate interest in astronomy and had built his own reflecting telescope with mirrors. He ground and polished himself. His dedication to systematic observation was remarkable. Night after night, he methodically examined different sections of the heavens, recording everything he saw with meticulous care. That particular evening, Herschel noticed an unusual object in the constellation Gemini. Unlike the stars around it, which appeared as perfect points of light, this object showed a small disk when viewed through his telescope. At first, he thought it might be a comet, but as he tracked it over the following nights and weeks, its behavior puzzled him. The object moved slowly and steadily, following a path that suggested something far more significant. Other astronomers across Europe turned their instruments toward this mysterious wanderer, and careful calculations of its orbit revealed an astounding truth. Herschel had discovered a new planet, the first to be found in recorded history. The discovery of Uranus, as it would eventually be named, doubled the known size of the solar system in a single moment. Here was a world nearly 2 billion miles from the Sun, invisible to the naked eye, patiently orbiting in the darkness, while generation after generation of humans had gazed at the stars unaware of its existence. The discovery electrified the scientific community and captured the public imagination. If one new planet could be found, might there be others waiting to be discovered? Herschel became famous overnight and received royal patronage that allowed him to dedicate himself fully to astronomy. With his sister Caroline working alongside him as an accomplished astronomer in her own right, Herschel embarked on ambitious surveys of the heavens. He built ever larger telescopes, including a massive 40-foot instrument that was the largest in the world at the time. Through these powerful instruments, Herschel catalogued thousands of stars, nebulae, and other celestial objects, creating maps of unprecedented detail and scope. As astronomers carefully tracked Uranus over the following decades, they noticed something peculiar. The planet's motion didn't quite match the predictions based on Newton's laws of gravity when only the known planets were considered. Uranus kept straying slightly from its predicted position, sometimes moving a bit faster than expected, sometimes a bit slower. These tiny discrepancies bothered astronomers who had come to trust in the precision of celestial mechanics. Two young mathematicians, working independently on opposite sides of the English Channel, came to the same radical conclusion. Perhaps another planet, even more distant than Uranus, was pulling on it with its gravity, causing these observed irregularities. In England, John Couch Adams performed extensive calculations in the early 1840s, attempting to determine where such a planet would need to be located to produce the effects seen in Uranus's orbit. In France, Urbain Le Verrier conducted similar mathematical work, refining his predictions throughout 1845 and 1846. Le Verrier sent his calculations to Johann Galler at the Berlin Observatory in September 1846, suggesting where to point a telescope to find the predicted planet. On the very first night of searching, September 23rd, Galler and his assistant Heinrich d'Arrest found a blue world almost exactly where Le Verrier's mathematics had indicated it should be. The discovery of Neptune represented a profound triumph of mathematical astronomy. Here was a planet discovered not by chance observation, but through pure calculation, found with pencil and paper before it was seen with a telescope. Neptune orbited at a distance of nearly 3 billion miles from the Sun, taking more than a century and a half to complete one orbit. Its discovery confirmed that Newton's laws of gravity operated even in the furthest reaches of the solar system, and demonstrated the power of mathematical prediction. The solar system had grown larger still, stretching out into the cold darkness far beyond what ancient astronomers had ever contemplated. Between the orbits of the known planets, astronomers discovered a multitude of smaller worlds. On the first day of the new century, January 1st, 1801, Giuseppe Piazzi in Sicily had discovered Ceres, a small body orbiting between Mars and Jupiter. Soon, other similar objects were found in the same region, and astronomers realized they had discovered the asteroid belt, a vast collection of rocky bodies that never coalesced into a single planet. Over the following decades, hundreds and eventually thousands of these minor planets were catalogued, adding new complexity to the solar system's structure. Comets. Those ghostly visitors that had inspired awe and fear throughout human history also became subjects of scientific study. Edmund Halley, a contemporary of Newton, had analyzed historical records of comet appearances and realized that bright comets seen in 1531, 1607, and 1682 might actually be the same object returning periodically. He predicted it would return again in 1758. Though Halley died before his prediction could be verified, the comet did indeed reappear, right on schedule. This periodic visitor became known as Halley's Comet, and its predictable returns demonstrated that these celestial wanderers followed the same gravitational laws as planets. Through the 18th and 19th centuries, larger telescopes revealed increasing detail on the planets themselves. Astronomers mapped the cloud bands of Jupiter and Saturn, observed the seasonal changes on Mars, and discovered numerous moons orbiting the giant planets. Each observation added to humanity's growing catalogue of the solar system's contents and characteristics. The Sun's family of worlds proved to be diverse and dynamic, with each planet possessing its own unique features and mysteries. By the latter half of the 19th century, the solar system had been mapped with impressive thoroughness. 8 major planets, dozens of moons, thousands of asteroids, and periodic comets populated a vast three-dimensional space centered on the Sun. Yet even as this cosmic neighborhood became familiar, astronomers understood that their knowledge remained incomplete. The distances were so vast, and the objects often so faint, that many discoveries surely remained to be made. The patient work of mapping would continue, generation after generation, slowly filling in the details of our celestial home. As the 19th century drew to a close, humanity possessed detailed maps of the solar system and understood the mathematical laws that govern celestial motion. Telescopes had revealed distant planets, countless stars, and mysterious nebulae swirling in the cosmic darkness. Yet despite all this knowledge, the heavens remained impossibly distant, separated from Earth by a void that seemed utterly impassable. The idea of actually traveling to these distant worlds appeared to belong purely to the realm of fantasy and imagination. It was during this period that a new breed of dreamers began to emerge. Writers who wielded not telescopes, but pens and typewriters. These authors of scientific romance, as the genre was then called, dared to imagine what earlier generations could scarcely contemplate: that humans might one day leave the surface of Earth and journey to other worlds. Their stories would do far more than merely entertain readers on quiet evenings. They would plant seeds of possibility in young minds, seeds that would eventually blossom into rockets, spacecraft, and the extraordinary achievements of the space age. In France, a writer named Jules Verne began publishing stories that combined scientific knowledge with boundless imagination. Verne had a particular gift for researching the latest scientific developments and extrapolating them into adventure narratives that felt almost plausible. In 1865, he published a novel titled From the Earth to the Moon, in which members of a Baltimore gun club conceived an audacious plan to send 3 men to the moon by firing them from an enormous cannon built in Florida. Verne chose his launch location with surprising foresight, selecting a site in Florida that lay not far from where, a century later, actual moon rockets would lift off from Cape Canaveral. Verne's story captured imaginations across Europe and America. He described in careful detail the preparation of the massive cannon, the construction of the aluminum projectile that would carry the voyages, and the calculations needed to achieve the correct trajectory. While a cannon could never actually launch people to the moon without crushing them with acceleration forces, Verne's attention to scientific detail made the story feel tantalizingly possible. He followed this novel with a sequel called Around the Moon, in which his travelers orbited Earth's natural satellite and observed its far side before returning home by splashing down in the Pacific Ocean, eerily presaging the Apollo mission's return procedure. These novels inspired countless readers to look up at the moon and wonder whether such journeys might truly happen someday. Young people who read Verne's books began to think differently about the barrier between Earth and space. Perhaps it was not an eternal, absolute boundary after all, but simply a very difficult problem awaiting a solution. Across the English Channel, another writer was crafting tales that would prove equally influential. Herbert George Wells, known as H.G. Wells, brought a different sensibility to scientific romance. Where Verne focused on engineering and the mechanics of space travel, Wells explored the philosophical and social implications of encountering other worlds and alien civilizations. In 1898, he published The War of the Worlds, describing an invasion of Earth by Martians fleeing their dying planet. The novel portrayed Mars as an ancient world where intelligent beings had developed technology far beyond humanity's achievements. Wells's Martians traveled between planets, not in cannon-fired projectiles, but in mysterious cylinders that crossed the void of space. While he provided fewer technical details than Verne, Wells sparked intense speculation about whether Mars or other planets might harbor life. His vivid descriptions of an alien civilization, desperate enough to cross interplanetary space, made readers contemplate humanity's place in a possibly crowded universe. The story also reversed the perspective, asking readers to consider Earth not as the center of creation, but as one planet among many, potentially vulnerable to visitors from beyond. Wells followed this success with The First Men in the Moon in 1901, imagining a journey to Earth's satellite using a fictional gravity-blocking substance called cavorite. The novel described lunar caverns inhabited by insect-like selenites living in a complex underground civilization. While the science was pure fantasy, the sense of wonder Wells evoked, the possibility of discovering utterly alien forms of life and society, resonated deeply with readers. He made space exploration feel not just like a technical challenge, but like a doorway to profound discoveries about life itself. These stories circulated widely, translated into numerous languages, and read by audiences around the world. In Russia, young Konstantin Tsiolkovsky read Verne's novels and felt his imagination ignited. In America, a boy named Robert Goddard climbed a cherry tree after reading Wells and looked up at the sky with new determination. In Germany, a young Werner von Braun devoured both authors' works and dreamed of making their visions real. The writers of scientific romance were creating something perhaps more important than entertainment. They were establishing a cultural permission to dream of space travel. Other writers joined this growing genre, each adding their own visions. In Britain, author Garrett P. Serviss wrote Edison's Conquest of Mars, imagining a retaliatory expedition to the Red Planet using electric spacecraft. Russian author Konstantin Tsiolkovsky himself wrote Beyond the Planet Earth, blending his theoretical knowledge of spaceflight with narrative fiction imagined space stations and trips to other worlds. These stories began to form a collective dream, a shared vision of humanity's future among the stars. What made these early science fiction works so powerful was their unique position at the intersection of imagination and possibility. They arrived at precisely the right moment in history. Humanity had recently witnessed extraordinary technological progress, railroads spanning continents, telegraph cables crossing oceans, electric lights illuminating cities, and the first powered aircraft taking flight. In this context of rapid advancement, the leap from Earth to space seemed difficult, but perhaps not impossible. The writers of scientific romance gave form to latent hopes and transformed vague wishes into specific, imaginable futures. The stories also performed a crucial function of making space travel seem inevitable rather than absurd. Before Werner and Wells, suggesting that humans might travel to other worlds would have seemed the height of foolishness. After their novels captured the popular imagination, space travel became a recognized aspiration, something that serious people might work toward. The dream had been legitimized, given shape and substance in the minds of millions of readers. As the 20th century dawned, these literary dreams began to inspire practical action. The writers of scientific romance had built a bridge between the astronomical knowledge carefully accumulated over centuries and the coming age of rockets and spacecraft. They had taken the distant lights in the night sky, those points of light that ancient astronomers had mapped and Renaissance scientists had explained, and transformed them into destinations, places that might actually be visited by future generations. The dream of space travel had begun in earnest, nurtured by stories told on quiet evenings, imagined adventures that would eventually inspire real ones. The boundary between fantasy and reality was about to blur in remarkable ways as dreamers became engineers and impossible visions began their slow transformation into metal, fuel, and fire. As the dawn of the 20th century approached, the dream of space travel remained just that, a dream captured in the pages of novels and the imaginations of visionaries. Yet somewhere in the quiet provincial town of Kaluga, Russia, a modest schoolteacher was about to transform fantasy into mathematical reality. His name was Konstantin Eduardovich Tsiolkovsky, and though he worked far from the prestigious universities and laboratories of the world's great cities, his mind soared beyond Earth's atmosphere to contemplate the principles that would one day carry humanity to the stars. Tsiolkovsky's path to becoming the father of astronautics was as unlikely as it was inspiring. Born in 1857 in a small village in Ryazan province, he lost much of his hearing to scarlet fever at the age of 10. This childhood illness, which might have limited another person's opportunities, instead drove young Konstantin deeper into the world of books and solitary contemplation. Unable to attend school in the conventional manner, he educated himself in his father's library, developing an extraordinary capacity for independent thought and mathematical reasoning. By his teenage years, Tsiolkovsky had already become fascinated with the possibility of traveling beyond Earth. He devoured the scientific romances of Jules Verne, but unlike most readers who simply enjoyed the adventures, he began to ask the fundamental question that would occupy much of his life. What would it actually take to escape Earth's gravitational embrace and venture into the cosmos? This question led him on a journey through physics, mathematics, and engineering principles that few had seriously considered for such a purpose. After passing his teaching examinations in Moscow, Tsiolkovsky took a position as a mathematics and physics teacher in Kaluga, a position he would hold for most of his working life. His modest salary and provincial circumstances did not dampen his cosmic ambitions. In the evenings and on weekends, in his small workshop at home, he conducted thought experiments and mathematical calculations that explored the mechanics of space travel. While his students learned geometry and algebra by day, their teacher spent his free hours calculating trajectories that would carry vehicles beyond the sky itself. In the 1880s and 1890s, Tsiolkovsky began publishing scientific papers on topics that seemed fantastical to his contemporaries. He wrote about the possibility of artificial satellites orbiting Earth, about space stations that might serve as waypoints for interplanetary travel, and about the physiological challenges humans would face in the weightless environment of space. These papers, published in obscure Russian journals, went largely unnoticed by the international scientific community, yet they contained insights that were decades ahead of their time. The crowning achievement of Tsiolkovsky's theoretical work came in 1903, the same year the Wright brothers achieved powered flight at Kitty Hawk. In that year, he published a paper titled The Exploration of Cosmic Space by Means of Reaction Devices, which contained what would become known as the Tsiolkovsky rocket equation. This elegant mathematical formula described the relationship between a rocket's velocity, the velocity of its exhaust, and the ratio of its initial mass to its final mass. In essence, Tsiolkovsky had discovered the fundamental principle that governs all rocket propulsion. A rocket moves forward by throwing mass backward at high speed. The equation itself was beautiful in its simplicity, yet profound in its implications. It revealed that to achieve the tremendous velocities needed to escape Earth's gravity, a rocket would need to carry an enormous amount of fuel relative to its payload. Tsiolkovsky calculated that a vehicle would need to reach a velocity of approximately 8 kilometers per second to orbit Earth, and 11 kilometers per second to escape Earth's gravity entirely. These numbers, which he derived through careful mathematical reasoning, remain the fundamental benchmarks for space travel to this day. But Tsiolkovsky did not stop with abstract calculations. He understood that for space travel to become real, practical technologies would need to be developed. He recognized that the solid fuel rockets that existed in his time, primarily used for fireworks and military signals, would never be powerful enough for the task. Instead, he proposed using liquid fuels, which could provide much higher exhaust velocities and could be controlled more precisely than solid rockets. He suggested combining liquid hydrogen and liquid oxygen as propellants, a combination that would indeed prove to be among the most efficient rocket fuels when it was finally used decades later. In his writings, Tsiolkovsky described multi-stage rockets that would discard empty fuel tanks as they climbed towards space, reducing their mass and increasing their efficiency. He envisioned gyroscopes and vanes in the rocket exhaust to control a spacecraft's orientation. He proposed pressurized cabins to protect space travelers from the vacuum of space. And he contemplated the challenges of providing air, water, and food for extended journeys. Many of these concepts, which seemed like pure science fiction to his contemporaries, would become standard features of the spacecraft built half a century later. Despite the brilliance of his work, Tsiolkovsky remained an isolated figure throughout much of his career. His deafness made communication difficult, and his location far from major scientific centers meant that few people encountered his ideas firsthand. He survived on his teacher's salary, often using his own modest funds to publish his papers and pamphlets. Recognition, when it came, arrived slowly. It was not until the 1920s, when he was already in his 60s, that the Soviet government began to acknowledge his contributions and provide him with a pension that allowed him to devote himself fully to his theoretical work. In his later years, Tsiolkovsky continued to expand his vision of humanity's future in space. He wrote about orbital stations that would rotate to create artificial gravity, about using solar energy to power spacecraft, and about the possibility of using space-based mirrors to illuminate cities or warm, cold regions of Earth. He contemplated journeys not just to the moon and planets, but to the stars themselves. In one of his most famous statements, he wrote, "Earth is the cradle of humanity, but one cannot live in a cradle forever." When Tsiolkovsky died in 1935, liquid-fueled rockets were still in their infancy, and space travel remained a distant dream. Yet the mathematical foundations he had laid were sound and complete. Future rocket engineers and space pioneers would follow the paths he had traced in his calculations, built on the principles he had established in his quiet study in Kaluga. The rocket equation that bore his name would be used to design every spacecraft that followed, from the first satellites to the mighty rockets that would carry humans to the moon. The story of Konstantin Tsiolkovsky reminds us that great advances often begin not in well-funded laboratories or prestigious institutions, but in the minds of individuals who dare to ask profound questions and persist in seeking answers despite obstacles and obscurity. A deaf schoolteacher in provincial Russia, armed with nothing but mathematics and imagination, had charted the course to the stars. While Konstantin Tsiolkovsky had provided the mathematical framework for spaceflight, proving that rockets could actually work required someone willing to build them with their own hands. That person emerged in the unlikely setting of rural Massachusetts, where a quiet physics professor named Robert Goddard dedicated his life to transforming rocket theory into reality. Born in 1882, Goddard grew up during an age when flight of any kind seemed fantastical. As a teenager, he climbed a cherry tree on his family's property and looked out over the meadows, imagining how wonderful it would be to build a device that could rise beyond the atmosphere. That moment in October 1899 became a turning point in his life, one he would commemorate every year afterward as his anniversary day, the day he committed himself to the dream of spaceflight. After earning his doctorate in physics, Goddard began conducting experiments with solid fuel rockets, the type that had been used for centuries in fireworks and military weapons. He quickly recognized their limitations. Solid fuel rockets burned inefficiently and couldn't be controlled once ignited. If rockets were ever to reach the velocities needed for space travel, they would require a more sophisticated approach. Goddard turned his attention to liquid fuels, which could be fed into a combustion chamber at controlled rates, allowing for throttling and even shutting down the engine if needed. He experimented with various combinations, ultimately settling on liquid oxygen and gasoline as his propellants. These substances, when mixed and ignited in a combustion chamber, produced tremendous thrust while remaining manageable enough for careful experimentation. Working largely in isolation, Goddard developed designs that seem obvious in hindsight, but were revolutionary at the time. He realized that rockets would work better in the vacuum of space than in the atmosphere, a fact that many educated people of his era doubted. Critics claimed that rockets needed air to push against, not understanding that rockets propelled themselves forward through Newton's third law, the action-reaction principle. For every molecule of hot gas expelled backward, the rocket moved forward with equal and opposite momentum. By the mid-1920s, Goddard was ready to attempt something no one had ever done before. In a workshop on his aunt's farm in Auburn, Massachusetts, he constructed a rocket that stood about 10 feet tall. The engine was mounted at the top, an unconventional arrangement that placed the fuel tanks below, like a bottle balanced on a flame. This design helped stabilize the rocket during flight. On March 16, 1926, a cold and clear New England day, Goddard transported his creation to the snow-dusted cabbage patch behind the farmhouse. His wife Esther stood ready with a camera to document the attempt. The rocket, slender and delicate-looking, rested in its launch frame while Goddard made final preparations with steady hands despite the cold. The ignition system sparked. For a moment, nothing seemed to happen as the engine warmed up. Then, with a roar that shattered the winter silence, the rocket lifted off. It rose into the air with surprising speed, climbing to a height of about 41 feet before arcing over and landing in the frozen field some distance away. The entire flight lasted only 2.5 seconds and covered a distance of about 184 feet. To an outside observer, it might have seemed like a modest achievement. The rocket had barely cleared the treetops and had flown for less time than it takes to draw a deep breath. Yet this brief flight represented something extraordinary. For the first time in human history, a liquid-fueled rocket had successfully launched and flown. The age of modern rocketry had begun, though few people knew it yet. Goddard continued his experiments with little fanfare and even less funding. He worked with a small team of assistants, methodically testing improvements to his designs. He developed systems for gyroscopic guidance that could keep a rocket stable during flight. He experimented with cooling systems that prevented the combustion chamber from melting under the intense heat of burning fuel. He designed multi-stage rockets, realizing that a vehicle could shed weight as it climbed by dropping empty fuel tanks. In 1929, one of Goddard's test flights attracted unwanted attention. The rocket rose higher and faster than before, creating a roar that alarmed nearby residents. Newspapers ran sensational stories about a moon rocket crashing in Worcester, and local authorities prohibited further tests in Massachusetts. This setback might have ended Goddard's work, but instead it led to an unexpected opportunity. Charles Lindbergh, fresh from his famous transatlantic flight, learned of Goddard's experiments and recognized their significance. Lindbergh helped arrange funding from the Guggenheim family, which allowed Goddard to move his operation to Roswell, New Mexico, where the wide open desert provided space for testing without disturbing neighbors. In the isolation of the New Mexico desert, Goddard and his small team made steady progress throughout the 1930s. His rockets grew larger and more sophisticated, reaching altitudes of more than 1.5 miles. He developed pumps that could feed propellants into the combustion chamber at high pressure, increasing efficiency. He refined his guidance systems, bringing his rockets closer to stable, controlled flight. Despite these achievements, Goddard remained relatively unknown to the public, and the significance of his work went largely unrecognized in his own country. He was a private man, protective of his patents and reluctant to share details of his designs. He published few papers about his later work, preferring to perfect his systems in secrecy. This caution meant that when other nations began developing rockets in earnest, they would largely have to rediscover what Goddard had already learned. During the Second World War, Goddard worked on developing rocket-assisted takeoff systems for aircraft, but his proposals for long-range rockets received little interest from military planners. Meanwhile, in Germany, engineers were building on similar principles to create weapons that would prove the potential and the danger of rocket technology. Goddard passed away in 1945, just days after the war ended in Europe, without seeing his life's work lead to the space age he had envisioned. Yet in the decades that followed, space engineers would look back at his patents and papers with astonishment, finding that this quiet professor had already solved many of the fundamental challenges of rocketry. His liquid-fueled engines, his guidance systems, his multi-stage designs, all would become standard features of the rockets that carried satellites and astronauts into orbit and beyond. The brief flight in that Massachusetts cabbage patch had indeed been the first step on humanity's journey to the stars. While Robert Goddard worked in relative isolation in the American countryside, across the Atlantic Ocean, another group of dreamers was pursuing the same vision, with very different resources. In Germany during the 1920s and 1930s, enthusiasm for spaceflight captured the imagination of engineers, scientists, and amateur rocketeers who formed societies dedicated to turning dreams of space travel into reality. The Verein für Raumschifffahrt, or Society for Space Travel, brought together some of the brightest minds interested in rocketry. Young engineers gathered at an abandoned ammunition storage area near Berlin called Raketenflugplatz, where they could safely test their experimental rockets. Among these enthusiastic pioneers was a tall, charismatic young man named Wernher von Braun, whose passion for spaceflight had been ignited as a teenager when he read Hermann Oberth's theoretical work on rocket propulsion. Von Braun possessed a rare combination of technical brilliance and the ability to inspire others with his vision. While still in his early 20s, his work caught the attention of the German military, which saw potential applications for rocket technology. In 1932, the army hired him to develop liquid-fueled rockets, providing resources far beyond what the amateur rocket societies could muster. This marked a turning point, as rocket development shifted from enthusiastic hobbyists to a well-funded military program. The army established a research facility at Peenemünde, a remote location on the Baltic coast, where secrecy could be maintained and rockets could be launched over water. Here, von Braun and a growing team of engineers worked to solve the countless technical challenges that had plagued early rocket experiments. They needed to create powerful engines that wouldn't tear themselves apart, guidance systems that could keep rockets on course, and structures light enough to fly yet strong enough to withstand tremendous forces. Progress came through methodical experimentation and learning from each failure. The team developed increasingly sophisticated rockets, designated with the letter A for aggregate, meaning assembly or apparatus. The A1 and A2 designs helped them understand combustion dynamics and stability. The A3 introduced a more advanced guidance system, though early tests revealed problems that required further refinement. Each prototype brought valuable lessons that informed the next design. By the late 1930s, the team was working on the A4, which would prove to be a revolutionary machine. This rocket stood nearly 50 feet tall and weighed over 12 tons when fueled. Its engine burned a mixture of liquid oxygen and alcohol, producing tremendous thrust. The engineers designed an intricate system of gyroscopes and graphite vanes positioned in the rocket's exhaust stream to control its flight path. The fuel pumps alone represented engineering marvels, spinning at thousands of revolutions per minute to feed the hungry combustion chamber. The first successful launch of the Aher-4 took place on October 3, 1942. The sleek rocket rose from its launch pad and climbed steadily into the autumn sky above Peenemünde. It ascended to an altitude of approximately 53 miles, crossing the boundary that many consider the edge of space, before arcing back down to splash into the Baltic Sea, nearly 120 miles away. For the first time in history, a human-made object had reached space and demonstrated controlled flight beyond the atmosphere. This achievement represented an extraordinary leap forward in rocket technology. The A4 could carry a payload beyond Earth's atmosphere and deliver it across vast distances. The military later gave it a different designation, the V2, standing for Vergeltungswaffe 2, or Vengeance Weapon 2. Between 1944 and 1945, thousands of these rockets were manufactured and launched, primarily targeting London and Antwerp. From a purely technical standpoint, the V2 demonstrated that many of the theoretical concepts proposed by Tsiolkovsky and tested by Goddard could indeed work at operational scale. The rocket featured innovations that would influence spacecraft design for decades to come. Its aerodynamic shape minimized drag during atmospheric flight. The turbopump system efficiently delivered propellants to the combustion chamber. The guidance system, though primitive by modern standards, showed that rockets could be steered during flight. As the conflict in Europe drew to a close in 1945, both American and Soviet forces raced to capture German rocket technology and the engineers who had created it. Teams of specialists searched for documents, hardware, and personnel associated with the rocket program. The Americans launched Operation Paperclip, which brought von Braun and more than 100 of his colleagues to the United States. The Soviets similarly recruited German engineers and relocated substantial equipment and documentation to their own territory. Von Braun and his team arrived in America and initially settled at Fort Bliss in Texas, where they helped the US Army understand and replicate V2 technology. Captured V2 rockets were transported across the ocean and launched from White Sands Proving Ground in New Mexico. These flights served multiple purposes: training American engineers in rocket operations, testing modifications and improvements, and conducting scientific experiments by carrying instruments to the edge of space. The captured V2s provided American scientists with unprecedented opportunities to study the upper atmosphere and the boundary of space. Researchers attached cameras, spectrometers, and other instruments to the rockets, gathering data that was previously impossible to obtain. These flights revealed information about cosmic rays, solar radiation, and atmospheric composition at extreme altitudes. Each launch built knowledge and experience that would prove invaluable in the years ahead. The German rocket program had demonstrated beyond doubt that reaching space was technically feasible. The V2, despite its origins and purposes, represented humanity's first practical vehicle capable of crossing the threshold between atmosphere and void. The engineers who created it had solved fundamental problems of propulsion, guidance, and control. They had shown that liquid-fueled rockets could be built large enough and powerful enough to carry significant payloads beyond the bonds of Earth. As the 1940s came to an end, the foundations were in place for the next phase of humanity's journey into space. The theoretical work of visionaries like Tsiolkovsky had been proven correct. The experimental courage of pioneers like Goddard had demonstrated that rocket engines could work. And now the V2 program had created an actual vehicle that could reach space. The pieces were falling into place, and the world was about to enter an entirely new era. In laboratories and military facilities across both America and the Soviet Union, engineers studied the lessons learned from Peenemünde and began planning vehicles that would go higher, faster, and farther than ever before. The world had never heard anything quite like it. On the evening of October 4th, 1957, a rhythmic beeping sound transmitted from space reached radio receivers across the globe. That simple signal, lasting less than a second and repeating every 0.3 of a second, announced that humanity had entered a new era. The sound came from a polished metal sphere just 22 inches in diameter, weighing about 184 pounds, circling Earth every 96 minutes at an altitude of nearly 600 miles. The Soviet Union had successfully launched Sputnik 1, the world's first artificial satellite, and nothing would ever be quite the same. The launch took place at the Baikonur Cosmodrome in the remote steppes of Kazakhstan. The rocket that carried Sputnik skyward was a modified version of the R-7 Semyorka, an intercontinental ballistic missile that the Soviet engineers had adapted for peaceful purposes. As the rocket climbed through the darkening sky, its engines roaring with over 1 million pounds of thrust, it carried not just a metal sphere, but the hopes and ambitions of an entire nation. When the satellite separated from the rocket's upper stage and began its orbit, ground stations tracked its path and confirmed that humanity had, for the first time, placed an object into continuous orbit around Earth. The satellite itself was elegantly simple. 4 long antennas extended from the polished sphere, trailing behind like whiskers as it sailed through the vacuum of space. Inside the pressurized shell, a radio transmitter, powered by batteries, sent out those famous beeps on 2 frequencies that amateur radio enthusiasts around the world could detect with basic equipment. The satellite also carried sensors to measure the density of the upper atmosphere and to detect micrometeoroids, though its primary purpose was to prove that launching and tracking a satellite was possible. News of the launch spread rapidly around the world. Radio stations interrupted their regular programming to broadcast the satellite signal. People gathered in their yards after sunset, scanning the sky for a glimpse of the tiny artificial moon as it caught the last rays of the sun and glinted like a moving star. Newspapers ran banner headlines announcing the achievement. At observatories and tracking stations, scientists and technicians worked around the clock to plot the satellite's orbit and analyze its telemetry. The age of space had arrived, and everyone wanted to witness it. The reaction in the United States was one of shock and concern. American scientists and engineers had been working on their own satellite program, Project Vanguard, but it had encountered numerous delays and technical challenges. The Soviet achievement came as a stunning surprise to much of the American public and government, who had assumed their nation held a clear technological advantage. The successful launch demonstrated sophisticated capabilities in rocketry, guidance systems, and engineering that many had not expected from the Soviet Union. Almost overnight, the peaceful competition to explore space took on new urgency. and became intertwined with Cold War tensions. Behind the Soviet success lay years of dedicated work by engineers and scientists who had been developing rocket technology since the end of the previous war. Led by chief designer Sergei Korolev, whose name would remain a state secret for years, the team had overcome countless technical obstacles. The R-7 rocket itself represented a remarkable achievement, with its distinctive cluster of engines and innovative staging system. Korolev had long dreamed of using rockets to reach space, and Sputnik represented the first step toward much grander ambitions. The pressure to succeed had been immense, with multiple test launches of the R-7 rocket experiencing failures before the successful flights that preceded Sputnik's launch. The satellite's batteries lasted for 22 days, during which time its beeping signal became the most listened to sound in the world. Even after the transmitter fell silent, the satellite continued to orbit, a silent testament to human achievement. Tracking stations followed its path for 3 months, until atmospheric drag gradually lowered its orbit. On January 4th, 1958, Sputnik 1 re-entered Earth's atmosphere and burned up over the Pacific Ocean, its mission complete, but its impact permanent. Less than a month after Sputnik 1, the Soviet Union followed up with an even more ambitious mission. On November 3rd, 1957, Sputnik 2 carried the first living creature into orbit, a dog named Laika. This much heavier satellite, weighing over 1,000 pounds, demonstrated that the R-7 rocket could lift substantial payloads and that life support systems could function in space. The missions proved that the dreams of space travel theorists like Tsiolkovsky and the practical experiments of rocket pioneers had culminated in a genuine capability to venture beyond Earth's atmosphere. The launch of Sputnik transformed space exploration from a distant dream into an immediate reality. Governments around the world recognized that the ability to reach orbit had profound implications for science, technology, and international prestige. Universities established new programs in aerospace engineering and space science. Young people looked at the sky with wonder, imagining futures where space travel might become commonplace. The satellite itself was a relatively simple device, but it represented something far more significant, proof that humans could extend their reach beyond the cradle of Earth. In the months following Sputnik's launch, the pace of space activity accelerated dramatically. The United States redoubled its efforts, and on January 31st, 1958, successfully launched Explorer 1, America's first satellite. That mission made an important scientific discovery, detecting the radiation belts surrounding Earth that would later be named after scientist James Van Allen. The Soviet Union continued with additional Sputnik missions, each one testing new technologies and pushing boundaries further. What had begun with a beeping sphere had sparked a sustained effort to explore the cosmos. The dawn of the space age also brought about new ways of thinking about humanity's place in the universe. For the first time, objects made by human hands orbited the planet as artificial moons. The view from space, though not yet seen by human eyes directly, could be imagined in new ways. The satellite's orbit, passing over different parts of Earth with each circuit, reminded people that national boundaries appeared differently from the cosmic perspective. Space was becoming not just a subject for telescopic observation, but a realm where humanity could operate and explore. As autumn turned to winter in 1957, the world had irrevocably changed. The successful launch of Sputnik had opened a door that would never close. The beeping signal that had captured the world's attention had announced more than just a technical achievement. It had proclaimed that the ancient dream of reaching beyond Earth was no longer fantasy, but fact. No longer someday, but now. The journey that had begun with ancient stargazers and progressed through centuries of scientific understanding had reached a milestone. Humanity had taken its first step off the planet, and the greatest adventure in human history was truly beginning. With Sputnik's successful orbit complete, the next great question facing scientists and engineers on both sides of the space race was whether living creatures could actually survive the journey into space. The vacuum beyond Earth's atmosphere presented countless unknowns. Could a living being withstand the violent acceleration of a rocket launch? Would the heart continue to beat properly in weightlessness? Could lungs draw breath in the artificial environment of a sealed capsule? Before any nation would risk sending a human into the cosmos, these questions needed answers. And so began one of the most remarkable chapters in the story of space exploration, when animals became our pioneers among the stars. The Soviet Union, building on their success with Sputnik, moved quickly to prepare for the next milestone. Less than a month after their first satellite circled the globe, they readied another spacecraft, this one carrying a passenger. On November 3rd, 1957, Sputnik 2 launched from the Baikonur Cosmodrome with a small dog named Laika secured inside a padded compartment. Laika was a stray terrier mix found wandering the streets of Moscow, selected partly because scientists believed street dogs had already learned to endure harsh conditions and stress. Her capsule contained systems to provide oxygen, food, and water, along with sensors to monitor her vital signs as she orbited high above the Earth. The world watched with intense interest as reports emerged about this canine cosmonaut. Laika survived the launch and the initial hours in orbit, proving that a living creature could indeed withstand the forces of reaching space. The data transmitted back to Earth showed her heart rate and breathing, providing invaluable information about how a mammal's body responded to weightlessness. Though Laika's mission could not bring her home safely, as the technology for re-entry had not yet been developed, her journey demonstrated that life could exist in the space environment, even if only briefly. She had opened the door for all the missions that would follow. The Soviets continued their biological space program with increasing sophistication. In 1960, two more dogs named Belka and Strelka rode into orbit aboard Sputnik 5, accompanied by a grey rabbit, 40 mice, 2 rats, and several plants and fungi. This time, the spacecraft carried a heat shield designed to protect the capsule during the fiery descent through the atmosphere. After a full day in space, completing 18 orbits of Earth, the capsule returned safely, and all the animals survived. Belka and Strelka became celebrities, appearing in newspapers around the world. Their successful return proved that recovery from space was possible, bringing human spaceflight one step closer to reality. Meanwhile, across the Atlantic, the United States pursued its own program of biological spaceflight research. American scientists chose to work primarily with primates because of their physiological similarity to humans. In December 1958, a squirrel monkey named Gordo rode a Jupiter rocket on a suborbital flight, soaring nearly 200 miles above the Earth before splashing down in the Atlantic Ocean. Though a malfunction prevented Gordo's recovery, telemetry data confirmed he had survived the flight into space and the subsequent minutes of weightlessness. The following year brought a more successful mission when a rhesus monkey named Abel and a squirrel monkey named Miss Baker flew together aboard another Jupiter rocket in May 1959. Their capsule reached an altitude of 300 miles and traveled downrange nearly 1,500 miles before splashing down in the ocean. Recovery ships retrieved the capsule quickly, and both monkeys were found in good condition. Miss Baker, in particular, lived for many years after her spaceflight, eventually residing at the U.S. Space and Rocket Center in Huntsville, Alabama, where visitors could see the tiny pioneer who had helped pave the way to space. As American preparations advanced toward human spaceflight, the choice of chimpanzees as test subjects became essential. Chimpanzees could be trained to perform tasks during flight, allowing scientists to assess whether mental and physical coordination remained intact in the strange environment beyond Earth's atmosphere. A young chimpanzee named Ham, originally from the jungles of Cameroon, underwent extensive training for his mission. He learned to pull levers and push buttons in response to flashing lights, receiving banana pellets as rewards for correct responses and mild signals when he made errors. On January the 31st, 1961, Ham rode a Mercury Redstone rocket on a suborbital flight that would closely simulate what a human astronaut would soon experience. Strapped into a specially designed couch inside the Mercury capsule, Ham ascended to an altitude of 157 miles. The flight lasted 16.5 minutes, during which Ham experienced approximately 6 minutes of weightlessness. Throughout the journey, he continued performing his trained tasks, proving that complex mental and physical functions remained possible even in the disorienting conditions of spaceflight. When the capsule splashed down in the Atlantic and recovery crews opened the hatch, they found Ham tired but healthy, happily accepting an apple and half an orange. Ham's successful flight provided NASA with the confidence to proceed with human missions. Yet the space program conducted one more chimpanzee flight before the end of 1961. A chimpanzee named Enos became the first primate to orbit Earth, completing 2 circuits of the planet aboard a Mercury capsule in November. The mission tested all the systems that would support astronaut John Glenn's orbital flight just a few months later. Enos performed his trained tasks throughout the flight, even when a malfunction in the equipment caused him to receive signals at incorrect times. His ability to adapt and continue working under these unexpected conditions impressed the mission controllers and demonstrated the resilience of living creatures in space. France also contributed to the biological exploration of space when they launched a cat named Félicette on a suborbital rocket flight in October 1963. With electrodes implanted to monitor her brain activity, Félicette provided unique data about neurological function during spaceflight. Her successful mission and recovery added another piece to the growing understanding of how different species responded to the space environment. These animal pioneers, representing many species from many nations, each contributed essential knowledge to humanity's venture into space. They tested life support systems, proved that living hearts could beat in zero gravity, demonstrated that breathing could continue in artificial atmospheres, and showed that consciousness and coordination persisted beyond Earth's protective embrace. The data gathered from their flights informed the design of spacecraft, the development of training programs, and the medical protocols that would keep human space travelers safe. As the various animal space programs wound down in the early 1960s, the stage was set for humanity's next great leap. The courage of these small ambassadors, who had no choice in their missions but served nonetheless, had illuminated the path forward. The engineers and physicians studying their telemetry now possessed the knowledge they needed to design systems that could keep humans alive in the harsh environment of space. The dreams that had animated science fiction writers and inspired rocket pioneers could now move from imagination toward reality, thanks in large measure to the animals who had ventured into the unknown first and shown us the way. The animal cosmonauts and astronauts had returned safely to Earth, their missions successful in proving that living beings could survive the journey beyond our atmosphere. Engineers and scientists had gathered invaluable data about weightlessness, radiation, and the challenges of life support systems. Now, with this knowledge in hand, the moment had arrived for humanity to take its most daring step yet. The time had come for a human being to leave Earth and see our planet as no one ever had before. In the Soviet Union, a group of young military pilots had been selected for a program shrouded in secrecy. They trained rigorously, preparing their bodies and minds for conditions no human had ever experienced. Among them was a man with a warm smile and calm demeanor, someone whose name would soon be spoken across every continent. Yuri Alexeyevich Gagarin, born in a small Russian village in 1934, had grown up during difficult times, yet he possessed an optimistic spirit and an unwavering determination. He had learned to fly jets in the Soviet Air Force, and now, at just 27 years old, he stood ready to journey where no human had ventured. The spacecraft that would carry him was called Vostok 1, a spherical capsule designed to protect a single person during the violent forces of launch and the fiery descent back through the atmosphere. Unlike the elaborate spacecraft that would come later, Vostok was relatively simple in its design. The cosmonaut inside would have limited control over the vessel. Instead, computers on the ground and automatic systems would guide most of the flight. This was, after all, a first attempt, and Soviet engineers wanted to minimize the variables that could go wrong. As dawn broke on April 12, 1961, at the Baikonur Cosmodrome in Kazakhstan, Gagarin rode to the launch pad in a bus with his backup crew. He wore a bright orange pressure suit designed to protect him if the cabin lost pressure during flight. Technicians and engineers who had worked countless hours to prepare for this moment watched as he climbed the tower to the top of the R-7 rocket. This same type of rocket had launched Sputnik nearly 4 years earlier, but now it would carry something infinitely more precious: a human life. Gagarin entered the cramped Vostok capsule and settled into the specially molded seat. Outside, the hatch was sealed shut. Through his radio, he could hear the voices of the launch controllers running through their final checks. Despite the historic nature of what was about to happen, Gagarin remained remarkably calm. Those monitoring his vital signs noted that his heart rate stayed steady, even as the countdown approached 0. When asked how he felt, he reportedly said he was ready and eager to begin. At just past 9 in the morning, Moscow time, The rocket engines ignited with a thunderous roar. The R-7 lifted slowly at first, then with increasing speed as it climbed into the clear sky. Gagarin felt the tremendous forces pressing him back into his seat as the rocket accelerated. Through his small viewport, he could see the Earth falling away below. The blue sky began to darken, transitioning to the deep black of space as the atmosphere thinned. Within minutes, the protective shroud around his capsule fell away, giving him an unobstructed view. And what a view it was! Gagarin became the first human to witness something that would change how our species understood our place in the universe. He saw Earth as a sphere, a beautiful blue and white marble suspended in the darkness. He observed the thin, delicate line of the atmosphere hugging the planet's surface. The curvature of the horizon stretched before him in a gentle arc. Through his radio, he transmitted his observations back to those listening on the ground, describing the colors, the clouds, and the overwhelming beauty of the sight. The rocket's upper stage shut down right on schedule, and Vostok 1 entered orbit approximately 10 minutes after launch. Gagarin was now traveling at more than 17,000 miles per hour, orbiting Earth at an altitude that varied between about 190 to 220 miles above the surface. He experienced weightlessness for the first time, feeling his body float against the restraints that held him in his seat. He tested his ability to move, to think, to perform simple tasks. Everything seemed to function normally, despite the absence of gravity's familiar pull. The single orbit lasted 108 minutes. During this time, Gagarin passed over oceans and continents, seeing Siberia, the Pacific, the southern tip of South America, and Africa. He made notes, took observations, and maintained communication with ground stations as they came into range. The automatic systems worked as designed, orienting the spacecraft for the critical engine burn that would slow it down and bring it back to Earth. The return journey presented its own challenges. The Vostok capsule had to withstand the intense heat generated as it plunged back into the atmosphere at tremendous speed. Gagarin felt the forces increase again, pressing him into his seat as the spacecraft decelerated. The exterior of the capsule glowed orange and red from the friction with air molecules. Communication was temporarily lost during this phase, a tense period for those monitoring the flight from below. At about 4 miles above the ground, following the mission plan, Gagarin ejected from the capsule. He and the spacecraft descended separately under parachutes, a design feature of the Vostok system. The spacecraft landed in a field, and Gagarin touched down safely not far away in the Saratov region of Russia. Local farmers working in their fields were startled to see this figure in an orange suit descending from the sky. Gagarin, ever friendly, assured them he was a fellow Soviet citizen who had just returned from space. News of the successful mission spread quickly. The Soviet Union announced Gagarin's achievement to the world, and celebrations erupted across the country. In Moscow, massive crowds gathered to welcome him home. He was awarded the title Hero of the Soviet Union and became an international celebrity overnight. People everywhere recognized his name and face. He traveled to numerous countries as an ambassador of Soviet space achievement, always gracious and humble despite the extraordinary thing he had accomplished. Gagarin's flight lasted less than 2 hours from launch to landing, but its impact resonated far beyond that brief time. He had proven definitively that humans could travel to space, orbit Earth, and return safely. The data from his mission confirmed that people could function effectively in weightlessness. His safe return demonstrated that re-entry systems could protect a cosmonaut from the extreme conditions of coming back through the atmosphere. The success of Vostok 1 intensified the space race between the Soviet Union and the United States. America had been working toward its own crewed flights, but the Soviets had reached this milestone first. The achievement motivated American effort and added urgency to the goal of catching up and eventually surpassing Soviet accomplishments. For Yuri Gagarin, life after his historic flight brought both honor and constraint. He became too valuable as a symbol to risk on another space mission. Though he continued to work in the space program and trained other cosmonauts, he never flew in space again. Tragically, his life ended in 1968 when the jet he was piloting crashed during a training flight. He was only 34 years old. Yet his legacy endures. Every April 12th is celebrated as Yuri's Night around the world, commemorating the anniversary of that first human spaceflight. His achievement opened the door through which hundreds of others would follow, each adding to our understanding and capability. The calm young man who smiled as he rode a rocket into the unknown had shown humanity that space was not just a realm for machines and instruments, but a place where people could go, explore, and return to tell the story. With Yuri Gagarin's successful journey around Earth still fresh in the world's imagination, the United States moved forward with determined purpose to answer the Soviet achievement. America's response would unfold through two distinct programs, each building upon the lessons of the last, each pushing the boundaries of what humans could accomplish beyond the atmosphere. The Mercury program represented America's first tentative steps into the cosmos. On May 12, 1961, just 3 weeks after Gagarin's orbital flight, astronaut Alan Shepard climbed into Freedom 7, a capsule barely large enough to contain him and his equipment. Unlike Gagarin's orbit around the planet, Shepard's flight would follow a simpler arc, launched on a Redstone rocket that would carry him in a high suborbital trajectory before bringing him back to Earth. For 15 minutes, Shepard experienced weightlessness and glimpsed the curvature of Earth against the blackness of space. Though brief, his journey proved that American technology could safely carry a human beyond the atmosphere and return him home. The excitement of that spring morning in 1961 rippled across America. Millions watched on television as the rocket ignited and climbed into the Florida sky. When Shepard splashed down in the Atlantic Ocean and reported himself in good condition, the nation celebrated its entry into human spaceflight. 3 months later, Gus Grissom repeated the suborbital achievement in Liberty Bell 7, though his capsule sank after splashdown when the hatch unexpectedly blew open. Grissom himself swam safely to the waiting helicopters, and the program continued forward. The real challenge still lay ahead. To truly match the Soviet achievement, an American astronaut needed to complete a full orbit of Earth. On February the 20th, 1962, John Glenn squeezed into Friendship 7 atop a more powerful Atlas rocket. The countdown proceeded with the entire nation watching anxiously. when the rocket's engines roared to life and the Atlas lifted off. Glenn became the first American to orbit the planet. 3 times he circled Earth, marveling at the view of continents and oceans passing beneath him, observing the thin blue line of atmosphere that protected all life below. Glenn's mission faced an unexpected challenge during the flight, when Mission Control received a signal indicating that his heat shield might have come loose. If the shield failed during re-entry, the capsule would burn up in the atmosphere. The astronaut received instructions to keep the retro rocket package attached during re-entry, rather than jettisoning it as planned, hoping this would help hold the shield in place. Glenn calmly followed procedures as flames flickered past his window during the fiery descent. The shield held, and the concern proved to be a false sensor reading. His safe splashdown marked another milestone achieved. 3 more Mercury missions followed through 1963, each staying aloft longer than the last. Scott Carpenter orbited Earth 3 times in Aurora 7. Wally Schirra completed 6 orbits in Sigma 7. Gordon Cooper pushed the program's limits with 22 orbits over 34 hours in Faith 7, demonstrating that humans could function in space for more than a day. Each flight taught valuable lessons about spacecraft systems, life support, and human adaptation to weightlessness. Yet the Mercury capsules, for all their success, offered limited capabilities. The astronaut inside had minimal ability to maneuver the spacecraft. The capsules could not change their orbits significantly or meet up with other vehicles in space. If America hoped to reach the moon, more sophisticated techniques would be required. A spacecraft would need to rendezvous with another craft, dock with it, and work as a combined vehicle. Astronauts would need to leave their capsules and work in the vacuum of space itself. The Gemini program emerged to master these complex skills. Named for the constellation of the twins, Gemini spacecraft carried 2 astronauts and offered far greater maneuverability than Mercury had provided. Between 1965 and 1966, 10 crewed Gemini missions launched from Cape Kennedy, each testing new techniques and pushing boundaries. On March 23, 1965, Gus Grissom and John Young flew the first crewed Gemini mission, demonstrating the spacecraft's ability to change its orbit using onboard thrusters. 3 months later, Ed White opened the hatch of Gemini 4 and floated out into space, becoming America's first spacewalker. Tethered to the spacecraft, White maneuvered using a handheld gas gun, while his crewmate James McDivitt photographed the historic moment. White's exhilaration was evident in his voice transmissions, and he expressed reluctance when the time came to return inside. The Gemini program systematically worked through its checklist of skills needed for lunar missions. Gordon Cooper and Pete Conrad stayed in space for 8 days aboard Gemini 5, proving that astronauts could endure missions long enough to travel to the moon and back. Frank Borman and Jim Lovell pushed the endurance record to 14 days in Gemini 7, though the long confinement in the tiny capsule tested their patience and comfort. Rendezvous operations proved challenging but achievable. Wally Schirra and Tom Stafford in Gemini 6 maneuvered their spacecraft to within a few feet of Gemini 7, still in orbit with Borman and Lovell aboard. The 2 capsules flew in formation, demonstrating the precise control possible. Later missions refined the technique until docking became routine. Neil Armstrong and David Scott achieved the first docking between 2 spacecraft when Gemini 8 successfully connected with an unmanned Agena target vehicle. Spacewalking, however, presented unexpected difficulties. After Ed White's successful first attempt, subsequent spacewalkers struggled with the physical demands of working in vacuum. Eugene Cernan became exhausted during a complex spacewalk from Gemini 9, his visor fogging from perspiration. The lack of friction and solid footing made even simple tasks surprisingly difficult. Astronauts and engineers worked to develop better techniques, improved spacesuits, and handholds that allowed more effective work outside the spacecraft. By the time the final Gemini mission launched in November 1966, the program had accomplished its goals. Astronauts had demonstrated they could work effectively in space for 2 weeks, perform rendezvous and docking operations, and complete spacewalks lasting several hours. The confidence gained from 20 spacecraft launches and 16 flights with crews aboard provided the foundation for the next great leap. The men who flew these missions came from test pilot backgrounds, accustomed to flying experimental aircraft and accepting calculated risks. They trained extensively in simulators, studied spacecraft systems until they could operate them instinctively, and prepared for every conceivable emergency. Their wives and children waited at home during launch countdowns and orbital operations, part of a national endeavor that captured the public imagination. As the Gemini program concluded, attention shifted to the massive rockets and sophisticated spacecraft being developed for lunar missions. The skills mastered during Mercury and Gemini would soon be applied to the most ambitious journey humans had ever attempted. The Moon, that silvery companion that had watched over Earth since before life emerged from the seas, would soon feel the touch of human footsteps on its ancient surface. As the Gemini program completed its final mission in November 1966, the groundwork had been laid for humanity's most ambitious journey. The astronauts had learned to walk in space, to guide their spacecraft with precision, to dock with other vehicles orbiting high above Earth. Yet these accomplishments were merely preparation for something far grander, a goal that had captured the imagination of the entire world. On May the 25th, 1961, President John F. Kennedy had stood before Congress and issued a challenge that seemed almost impossible. He called upon the nation to commit itself to landing a man on the moon and returning him safely to Earth before the decade's end. At that moment, America's total experience with human spaceflight consisted of a single 15-minute suborbital hop. No one had yet orbited Earth in an American spacecraft. No rendezvous had been attempted. No one knew if humans could even survive the journey to the moon and back. Yet Kennedy's words set in motion the largest peacetime mobilization of resources and personnel in the nation's history. The program that would answer this challenge took its name from the ancient Greek god who drove the chariot of the sun across the sky each day. Apollo would become synonymous with human achievement, with exploration, with reaching beyond what seemed possible. But in those early years of the 1960s, Apollo was a concept, a dream that required the invention of entirely new technologies and the solution of countless problems that no one had faced before. The first challenge was perhaps the most fundamental: how to actually get to the moon. Engineers debated 3 different approaches. Some advocated for direct ascent, building a rocket so powerful it could launch from Earth, fly straight to the moon, land there, and return home. Others proposed Earth orbit rendezvous, where multiple rockets would launch components that would assemble in orbit before departing for the Moon. The method that ultimately prevailed was lunar orbit rendezvous, a concept that seemed almost too complex to work, but offered crucial advantages in efficiency and weight. Lunar orbit rendezvous required the development of two separate spacecraft that would work in concert. The command and service module would carry 3 astronauts to the Moon and back, serving as their home for the week-long journey through space. Connected to it for most of the voyage would be the lunar module, a strange-looking craft designed to operate only in the vacuum of space and on the Moon's surface, where there was no air to create aerodynamic considerations. 2 astronauts would descend to the lunar surface in this fragile-looking vehicle, while the third remained in orbit, waiting for their return. To launch these spacecraft, engineers at the Marshall Space Flight Center in Huntsville, Alabama, began designing the most powerful rocket ever conceived. The Saturn V would stand 36 stories tall, taller than the Statue of Liberty, from ground to torch. When fully fueled, it would weigh 6 million pounds, most of that weight in the form of kerosene, liquid hydrogen, and liquid oxygen that would burn in carefully controlled explosions to produce thrust. The first stage alone contained 5 F1 engines, each producing more power than all the Atlases and Titans that had launched previous spacecraft combined. The roar of these engines at ignition could be heard from miles away, and the vibrations they created shook the ground like an earthquake. Every component of the Saturn V pushed the boundaries of what was technically possible. The fuel pumps for the F1 engines moved propellant at rates that would drain a swimming pool in seconds. The intricate plumbing that fed fuel and oxidizer required welding of unprecedented precision, because a single leak could cause catastrophic failure. The guidance systems needed to point this massive vehicle with incredible accuracy, threading it through a narrow corridor that would allow it to reach the Moon hundreds of thousands of miles away. Meanwhile, teams at North American Aviation worked on the command and service module. The conical command module, measuring about 12 feet across at its base, would be home for 3 men for up to 2 weeks. Every system had to be reliable, because there would be no rescue possible if something failed in deep space. The heat shield on the bottom had to withstand temperatures of 5,000 degrees Fahrenheit during re-entry into Earth's atmosphere. The service module carried the main rocket engine for course corrections, fuel cells that generated electricity by combining hydrogen and oxygen, and supplies of air and water. The lunar module presented unique engineering challenges. It had to be as light as possible, because every pound that landed on the Moon required many pounds of fuel to get it there. The skin of the spacecraft was so thin in places that engineers joked you could poke a screwdriver through it. Yet this delicate craft had to protect its crew and function perfectly in the hostile environment of space. It required 2 separate rocket engines, one for landing and one for returning to lunar orbit, and each had to work on the first try with no possibility of testing beforehand. Across the country, hundreds of thousands of people contributed to Apollo. Contractors in dozens of states manufactured components ranging from tiny electronic circuits to massive rocket stages. Seamstresses stitched together spacesuits with 21 layers of fabric, each layer serving a specific purpose in protecting astronauts from the vacuum, temperature extremes, and radiation of space. Computer programmers wrote code for the guidance systems, working with machines that had less computing power than a modern cell phone yet needed to navigate across the void between worlds. Test facilities sprang up to verify every aspect of the mission. Giant thermal vacuum chambers simulated the harsh environment of space. Centrifuges spun crew members to prepare them for the forces of launch and re-entry. Training spacecraft allowed astronauts to practice the delicate task of landing on the moon, hovering on rocket thrust above the simulated lunar landscape. The effort cost more than $24 billion, an enormous sum at the time. At its peak, Apollo employed over 400,000 people. Universities conducted research into everything from the effects of radiation on human tissue to the properties of lunar soil that no one had yet seen up close. The program drove innovation in fields far beyond aerospace, developing new materials, manufacturing techniques, and quality control procedures that would find applications throughout industry. By 1968, the pieces were coming together. Unmanned test flights had verified the Saturn V's performance. The command and service module had flown in Earth orbit. The lunar module was nearly ready. Astronauts had been selected and trained for the missions that would attempt the landing. Everything was converging toward that deadline Kennedy had set. That promise to reach the moon before 1970 arrived. The journey from Kennedy's challenge to the brink of actually attempting a lunar landing had taken 7 years of unprecedented effort, from drawing boards to test stands, from computer simulations to astronaut training. The Apollo program represented humanity organizing itself to accomplish something that had lived only in dreams and stories for thousands of years. The hardware was almost ready. The crews were prepared. Soon, the time would come to attempt what had once seemed impossible. The vast machinery of the Apollo program had been assembled, tested, and refined through years of dedicated effort. Now, in the summer of 1969, everything converged toward a single moment in history. The Saturn V rocket stood on Launch Complex 39A at Kennedy Space Center in Florida, a towering monument to human ambition reaching 363 feet into the sky. Inside the command module at its summit, 3 astronauts prepared for a journey that had captivated imaginations since the dawn of human consciousness. Neil Armstrong, Edwin Buzz Aldrin, and Michael Collins had trained for years, practicing every procedure until each movement became second nature. They had studied geology to recognize important lunar features, rehearsed equipment operations in simulators that replicated the lunar environment, and prepared for countless contingencies. On the morning of July 16, 1969, they rode the elevator to the top of the launch tower, walked across the access arm, and settled into their seats atop 7.5 million pounds of thrust. The countdown proceeded with mechanical precision through the final minutes. At 9:32 in the morning Eastern Time, the 5 massive F1 engines of the first stage ignited in sequence, releasing a controlled inferno of flame and sound. The hold-down arms released, and the entire stack lifted away from the launch pad with a grace that belied its enormous mass. Millions watched in person from the beaches and roads surrounding the Space Center, while hundreds of millions more followed the ascent on television screens around the world. The journey to the moon required 3 days of coasting through the void between worlds. The astronauts lived in the cramped confines of the command module, which they had named Columbia, monitoring systems and making small course corrections as they traveled. Behind them, Earth gradually shrank from filling their windows to becoming a blue and white sphere, then a marble suspended in the cosmic darkness. Ahead, the moon grew from a distant disk to a vast landscape of craters and mountains. On July 19th, they fired their service propulsion engine to slow down and enter lunar orbit. For the first time, human eyes looked directly upon the far side of the moon, that hemisphere forever hidden from Earth-bound observers. The surface below them appeared ancient and weathered, bearing the scars of billions of years of meteorite impacts. They circled the moon, photographing potential landing sites and preparing for the next crucial phase. Armstrong and Aldrin crawled through the tunnel connecting Columbia to the lunar module, which they had named Eagle. On July 20th, after checking all systems, they separated from the command module. Collins would remain in lunar orbit, maintaining the communications relay and preparing for the rendezvous that would bring his crewmates home. For the next 24 hours, he would be utterly alone, the most isolated human being in existence, orbiting the moon while his companions descended to its surface. The Eagle fired its descent engine to drop out of orbit and begin the powered descent to the surface. Armstrong and Aldrin stood at their stations, facing the forward windows, as the computer guided them down. At about 7,000 feet, alarms began sounding in the cabin. The computer was being overloaded with data, triggering warning lights that threatened to abort the landing. Mission Control quickly analyzed the situation and determined the alarms could be safely ignored. The descent continued. As they dropped below 2,000 feet, Armstrong realized the computer was guiding them toward a crater filled with boulders the size of cars. Terrain too rough for a safe landing. He switched to manual control and flew the lunar module like a helicopter, searching for a smoother spot. The fuel gauge showed precious seconds of propellant remaining. Dust began billowing up from the surface, stirred by the descent engine's exhaust, obscuring their view of the ground. At Mission Control in Houston, controllers watched their displays with mounting tension as the fuel level dropped lower and lower. The rules called for an abort if they hadn't landed by the time only 30 seconds of fuel remained, but calling an abort during the final moment carried its own risks. The room fell silent, except for the voices calling out altitude and fuel readings. Then, at 4:17 in the afternoon, Eastern Time, on July the 20th, 1969, a soft bump signaled contact with the lunar surface. Armstrong's voice came across the radio, calm and steady. "Houston, Tranquility Base here. The Eagle has landed." In the control room, controllers erupted in cheers and applause. They had done it. 2 human beings sat safely on the surface of the moon. The flight plan called for the astronauts to rest before venturing outside, but no one seriously expected them to sleep. After checking their systems and preparing their equipment, Armstrong opened the hatch and slowly backed out onto the small porch at the top of the ladder. A television camera mounted on the lunar module's side transmitted grainy black and white images to Earth, showing Armstrong's white-suited form climbing down the 9 rungs. At the bottom, a circular footpad rested on the lunar surface. Armstrong stepped off onto the fine-grained soil, and spoke the words he had composed during the journey. That's one small step for man, one giant leap for mankind. The audio was imperfect, and debate would continue for decades about whether he had said a man or simply man. But the meaning was clear. Humanity had arrived at another world. Aldrin joined him 19 minutes later, describing the alien landscape as magnificent desolation. Together, they unveiled a plaque mounted on the lunar module's leg that read, "Here men from the planet Earth first set foot upon the moon, July 1969 AD. We came in peace for all mankind." They planted an American flag, its horizontal rod holding it extended in the airless environment where no wind would ever blow. The two astronauts spent 2.5 hours outside, collecting 47 pounds of rocks and soil samples, setting up scientific instruments, and taking photographs. They moved in the 1/6 gravity with a distinctive bounding gait, part walk and part hop. Everything took longer than expected in their pressurized suits, and they worked steadily to complete their tasks before returning to the lunar module. Back inside Eagle, they rested briefly before firing the ascent engine to launch themselves back into orbit. The ascent stage lifted off perfectly, leaving the descent stage behind as humanity's first permanent installation on another celestial body. The rendezvous with Collins in Columbia went smoothly, and the three astronauts began their journey home, carrying with them the rocks, photographs, and memories of an achievement that had seemed impossible just a decade earlier. They splashed down in the Pacific Ocean on July 24th, completing a journey of just over 8 days. The achievement of Apollo 11 represented the culmination of centuries of astronomical observation, decades of rocket development, and years of focused effort by hundreds of thousands of people. More Apollo missions would follow, each contributing new knowledge about our nearest neighbor in space, but none would carry quite the same weight as that first landing, when humanity took its initial steps on another world. Following the triumph of reaching the lunar surface, humanity faced a new question. Could we not just visit space, but truly live there? The answer would emerge gradually through a series of remarkable orbital laboratories that transformed brief visits into extended stays among the stars. The Soviet Union pioneered this vision with Salyut 1, launched on April 19, 1971. This cylindrical station, nearly 50 feet long, became humanity's first space station to reach orbit successfully. The name Salyut, meaning salute, honored both Yuri Gagarin and the ongoing spirit of space exploration. When the first crew arrived aboard Soyuz 11 in June 1971, they inhabited the station for 23 days, conducting experiments and proving that humans could indeed function in a weightless home among the stars. They grew plants, observed Earth's atmosphere, and tested their bodies' responses to prolonged weightlessness. Though their mission ended in sorrow when the crew perished during re-entry due to a cabin depressurization, their time aboard demonstrated the possibilities of orbital living. The Soviets continued developing their Salyut program through the 1970s and early 1980s, launching 6 more stations. Each iteration improved upon the last, adding scientific instruments and refining life support systems. Cosmonauts gradually extended their stay durations, learning how to maintain their health during longer missions through exercise routines and careful diet planning. These crews became pioneers of a new lifestyle, adapting human routines to an environment where there was no up or down, where water floated in spheres, and where sleeping required being strapped to a wall. Meanwhile, America launched its own orbital laboratory. Skylab lifted off on May 14, 1973. Converted from the third stage of a Saturn V rocket into a surprisingly spacious station. The interior volume dwarfed the Soviet stations, providing nearly 12,000 cubic feet of living space. The launch itself nearly spelled disaster when a protective shield tore away, taking one of the solar panels with it and jamming the other. The first crew that arrived 11 days later faced the challenge of deploying a makeshift sunshade to prevent the station from overheating, a delicate repair performed during a spacewalk. Their success saved the mission. 3 crews inhabited Skylab between 1973 and 1974, with the final mission lasting an impressive 84 days. The astronauts conducted extensive observations of the Sun through a sophisticated solar telescope, capturing unprecedented images of solar flares and coronal activity. They photographed Earth below, documenting weather patterns, geological features, and environmental changes. They studied their own bodies, discovering how bones lost density and muscles weakened in the absence of gravity's constant pull. The astronauts also discovered the simple joys of orbital living, from watching thunderstorms roll across continents to performing acrobatic flips through the station's spacious workshop. The Soviets achieved their greatest triumph in space station development with Mir, which means peace or world in Russian. The core module launched on February 20th, 1986, beginning what would become a continuously inhabited orbital complex for over a decade. Unlike previous stations designed as single units, Mir was modular, with additional sections added over time, like rooms being built onto a house. Between 1987 and 1990, 5 additional modules docked to the core, each bringing specialized capabilities. Kavant 1 enhanced astronomical observations. Kavant 2 provided an airlock for spacewalks and additional life support. Crystal carried furnaces for material science experiments. Spectre and Peroda added Earth observation instruments and additional research facilities. Life aboard Mir settled into rhythms that balanced work with the needs of human well-being. Cosmonauts followed schedules that included exercise sessions on treadmills and stationary bicycles, fighting against the muscle and bone loss that plagued long-duration missions. They conducted thousands of experiments, growing crystals in microgravity that formed with perfection impossible on Earth, testing new materials and technologies, and observing how living organisms adapted to weightlessness. They welcomed visiting crews from many nations, as Mir became an international meeting place in orbit. French, German, British, Japanese, and eventually American astronauts traveled to the station, foreshadowing the cooperation that would define humanity's next orbital home. The longest single spaceflight in history occurred aboard Mir when cosmonaut Valery Polyakov remained in orbit for 437 consecutive days, from January 1994 to March 1995. His mission provided invaluable data about human endurance in space, demonstrating that properly conditioned individuals could potentially withstand the journey to Mars and back. Despite the extended isolation and confinement, Polyakov remained healthy and even walked unaided after landing, though Earth's gravity felt crushing after more than a year of weightlessness. Mir's later years brought challenges. Equipment aged. Systems required constant maintenance, and unexpected problems tested the crew's resourcefulness. In 1997, an unmanned Progress supply ship collided with the station during a docking test, puncturing the Spectre module and forcing the crew to seal it off. Despite these difficulties, Mir persisted, its systems patched and repaired by determined crews who refused to abandon their orbital home. The knowledge gained from Salyut, Skylab, and Mir proved invaluable. Engineers learned which systems needed redundancy, which materials withstood the harsh space environment, and how to design living quarters that supported psychological well-being during isolation. Medical researchers documented how the human body changed during extended weightlessness and developed countermeasures to minimize these effects. Scientists discovered which experiments benefited most from the unique environment of orbit, from protein crystal growth to combustion studies impossible under gravity's influence. These early space stations also revealed the profound psychological dimensions of orbital living. Crews described the overview effect, a cognitive shift that occurred when viewing Earth from above, seeing the planet as a single fragile sphere without visible borders. They spoke of the beauty that never faded, watching 16 sunrises and sunsets each day as the stations circled the globe every 90 minutes. They formed bonds with their crewmates, born from shared isolation and mutual dependence. And they missed simple things: the feel of wind, the smell of rain, the presence of family. As Mir aged toward the end of the 1990s, plans were already underway for something far more ambitious. The lessons learned from these pioneering stations would inform the design of a much larger orbital complex, one that would require the cooperation of multiple nations and represent humanity's commitment to a permanent presence among the stars. The era of experimental space stations was giving way to something more enduring, a true home in the heavens, where the work of understanding space and our place in it would continue for generations to come. The dream of reusable spacecraft would soon make journeys to this new station routine, transforming orbital construction and operations in ways the early pioneers could scarcely have imagined. As the space stations orbited quietly above Earth, demonstrating that humans could indeed live and work beyond our planet for months at a time, engineers and planners were already envisioning something revolutionary. What if a spacecraft could journey to orbit and return home, not as a one-time visitor, but as a reusable vehicle that could fly again and again, much like an aircraft? This question sparked the development of one of the most ambitious projects in the history of space exploration. The Space Shuttle program emerged from a desire to make access to space more routine and economical. Traditional rockets were expensive, used only once, and then discarded into the ocean or left as debris. The concept of a reusable spacecraft promised to transform spaceflight from rare, costly expeditions into something closer to regular operations. Throughout the 1970s, thousands of engineers worked to turn this vision into reality, designing a vehicle unlike anything that had flown before. The Space Shuttle was a remarkable hybrid. It would launch vertically like a rocket, maneuver in orbit like a spacecraft, and return to Earth, gliding through the atmosphere like an unpowered aircraft. The orbiter itself, about the size of a small airliner, would be attached to an enormous external fuel tank and 2 solid rocket boosters for launch. After reaching orbit, the orbiter would operate independently for days or weeks before returning home to land on a runway. On April 12, 1981, exactly 20 years after Yuri Gagarin's historic flight, the Space Shuttle Columbia lifted off from Kennedy Space Center in Florida. Commander John Young and pilot Robert Crippen rode the powerful thrust skyward, watching as the white, solid rocket boosters fell away and the massive orange external tank separated. Columbia entered orbit successfully, and 2 days later, Young guided the orbiter through the fiery descent back to Earth's atmosphere. The shuttle touched down on the dry lake bed at Edwards Air Force Base in California, proving that this extraordinary concept actually worked. The shuttle era transformed what was possible in space. The orbiter's large cargo bay could carry satellites, scientific instruments, and eventually massive components for building a space station. Astronauts could deploy satellites directly from orbit, and in some cases, they could even retrieve and repair satellites that had malfunctioned. The shuttle made it possible for crews of up to 7 astronauts to fly together, including scientists and engineers who weren't traditional test pilots. Over the following years, the fleet grew. Columbia was joined by Challenger, Discovery, Atlantis, and later, Endeavour. Each orbiter flew multiple missions, proving the reusability concept. The shuttle deployed the Hubble Space Telescope in 1990, placing this remarkable observatory into orbit where it would revolutionize astronomy by peering deep into the cosmos without the blur of Earth's atmosphere. When Hubble's initial images revealed a flaw in its primary mirror, the shuttle made possible something unprecedented. Astronauts flew to the telescope, installed corrective optics, and transformed it into the powerful instrument it was meant to be. The shuttle program excelled at conducting scientific research in the unique environment of space. The Space Lab module, carried in the cargo bay, served as a temporary orbital laboratory where astronauts performed experiments in biology, materials science, and medicine. Researchers on the ground could communicate directly with astronauts conducting their experiments in weightlessness, gathering data impossible to obtain on Earth. Perhaps the shuttle's greatest achievement was making possible the construction of the International Space Station. Beginning in 1998, shuttle missions carried enormous station modules, solar arrays, and other components into orbit. Astronauts performed intricate spacewalks to connect these pieces, assembling humanity's largest structure in space. The shuttle's robotic arm, a Canadian contribution, could lift and position massive objects with precision, making the complex assembly work feasible. Throughout its 30 years of operation, the Space Shuttle program demonstrated both the possibilities and the challenges of spaceflight. The program experienced profound tragedy, with the loss of Challenger in 1986 and Columbia in 2003, reminding everyone involved that venturing into space remained an undertaking of considerable complexity and risk. These experiences led to improvements in safety procedures and technical systems, and the program continued with renewed dedication to its mission. The shuttle carried astronauts from many nations, truly internationalizing human spaceflight. Scientists, doctors, and engineers who had dreamed of flying in space found opportunities aboard shuttle missions. The program deployed satellites for communications and Earth observation, conducted repairs in orbit, and performed countless experiments. Each mission added to humanity's understanding of working in the space environment. As the program matured, the shuttle became a familiar sight to the public. Launches from Florida's coast drew crowds of spectators who gathered on beaches and roadsides to watch the brilliant flame of the solid rocket boosters carry the orbiter skyward. Landing day brought its own excitement as the orbiter appeared in the sky, trailing twin sonic booms before touching down precisely on the runway. The reusability concept, while groundbreaking, proved more complex and costly than initially envisioned. Each orbiter required extensive maintenance and refurbishment between flights. The heat-resistant tiles that protected the vehicle during the scorching heat of re-entry needed careful inspection and often replacement. The sophisticated systems demanded meticulous attention. Nevertheless, the shuttle fleet flew 135 missions, spending over 1,000 days in space combined. When the Space Shuttle program concluded in 2011, it left behind an extraordinary legacy. The International Space Station stood complete, a testament to what the shuttle had made possible. Hundreds of satellites had been deployed. Scientific knowledge had expanded through countless experiments. An entire generation of astronauts had trained and flown aboard these remarkable vehicles. The shuttle era demonstrated that spacecraft could be designed for multiple missions, that complex construction could be accomplished in orbit, and that space could serve as a laboratory for discovery. The program's experiences, both triumphs and challenges, informed the next generation of spacecraft designers. As the final shuttle rolled to a stop on the runway, the lessons learned would guide future efforts to reach beyond Earth orbit, to return to the Moon, and eventually to venture to Mars. The age of reusable spacecraft had begun, and though the shuttle itself had completed its mission, the dream of routine access to space continued to inspire those planning humanity's next steps among the stars. As the Space Shuttle program transformed human spaceflight into something almost routine, another revolution was unfolding quietly across the solar system. While astronauts worked in orbit around Earth, robotic spacecraft ventured to destinations where no human could yet travel, becoming our eyes and instruments in the vast darkness beyond our world. These mechanical explorers began their journeys modestly. In the early 1960s, simple probes attempted to reach the Moon and nearby planets, though many failed or missed their targets entirely. Yet with each attempt, engineers learned and improved their designs. The Mariner spacecraft became some of the first successful planetary explorers, with Mariner 2 flying past Venus in 1962 and revealing a world of crushing atmospheric pressure and scorching temperatures hidden beneath perpetual clouds. Mariner 4 reached Mars in 1965, sending back the first close-up images of another planet's surface and showing a cratered, apparently lifeless landscape that challenged romantic notions of Martian civilizations. The twin Voyager spacecraft, launched in 1977, embarked on perhaps the most ambitious robotic journey ever conceived. Taking advantage of a rare planetary alignment that occurs only once every 176 years, these spacecraft were designed to visit Jupiter, Saturn, Uranus, and Neptune in a single grand tour of the outer solar system. Voyager 1 flew past Jupiter in 1979, capturing images of swirling storms and discovering active volcanoes on the moon Io, the first volcanism ever observed beyond Earth. It continued to Saturn, where its cameras revealed intricate structures in the planet's rings, and studied the mysterious moon Titan with its thick atmosphere. Voyager 2 followed a different path, becoming the only spacecraft to visit Uranus and Neptune. At Uranus in 1986, it found a world tipped on its side with faint rings and dark moons. At Neptune in 1989, it discovered a dynamic atmosphere with the fastest winds in the solar system and observed geysers erupting on the moon Triton. Both Voyager spacecraft continue traveling outward, now in interstellar space, carrying golden records with sounds and images from Earth as messages to any civilization that might find them millions of years from now. Mars drew particular attention from robotic explorers. Viking 1 and 2 landed on the Red Planet in 1976, becoming the first spacecraft to successfully operate on the Martian surface. Their cameras showed rust-colored rocks and pink skies, while their instruments analyzed the soil and searched for signs of life. Though the biology experiments produced ambiguous results, the Viking landers operated for years, measuring weather patterns and seasonal changes on an alien world. After a long gap in Mars exploration, the 1990s brought renewed focus to the Red Planet. Mars Pathfinder landed in 1912 with a small rover named Sojourner that drove across the surface, analyzing rocks and demonstrating that mobile exploration was possible. This success paved the way for increasingly sophisticated rovers. Spirit and Opportunity landed in 2004, designed to operate for 90 days, but exceeding all expectations. Opportunity continued exploring for nearly 15 years, traveling over 28 miles and discovering evidence that water once flowed across the Martian surface. The Curiosity rover, landing in 2012, brought the most advanced mobile laboratory ever sent to another world. The size of a small car and powered by a nuclear battery, Curiosity explored Gale Crater and climbed the slopes of Mount Sharp, drilling into rocks and analyzing their composition. Its discoveries confirmed that ancient Mars had conditions suitable for microbial life, with evidence of lakes, streams, and the chemical building blocks necessary for life as we know it. Beyond Mars, robotic explorers ventured to the solar system's other fascinating destinations. The Galileo spacecraft orbited Jupiter from 1995 to 2003, studying the giant planet and its moons in unprecedented detail. Its observations of Europa revealed a smooth, icy surface crisscrossed with cracks, suggesting a liquid ocean beneath the ice that might harbor life. The Cassini mission spent 13 years orbiting Saturn from 2004 to 2017, revolutionizing our understanding of the ringed planet and its many moons. It deployed the Huygens probe, which parachuted through the atmosphere of Titan and landed on its surface, revealing a world with lakes and rivers of liquid methane and ethane. Smaller worlds also received attention. The Near-Shoemaker spacecraft orbited and eventually landed on the asteroid Eros in 2001, the first soft landing on an asteroid. This mission demonstrated that asteroids were not loose collections of rubble, but solid bodies with complex histories. The Dawn mission visited both Vesta and Ceres, the two largest objects in the asteroid belt, discovering bright spots on Ceres that might be salt deposits from a subsurface ocean. Perhaps most remarkably, the New Horizons spacecraft completed a journey of over 9 years to reach Pluto in 2015 during its brief flyby, New Horizons revealed a complex world with nitrogen ice plains, water ice mountains, and a blue atmospheric haze. The heart-shaped region on Pluto's surface captured public imagination, transforming this distant world from a fuzzy dot in telescopes to a place with geography and weather. New Horizons continued into the Kuiper Belt, flying past a small, elongated object named Arrokoth on New Year's Day 2019, the most distant world ever visited by a spacecraft. Closer to home, numerous spacecraft studied our nearest neighbor, the Moon, including missions that discovered water ice in permanently shadowed craters near the poles. Other probes visited comets, including the Rosetta mission that orbited comet Churyumov-Gerasimenko and deployed a lander to its surface, revealing these icy wanderers as complex worlds rather than simple dirty snowballs. Each of these robotic explorers operated far from Earth, often receiving commands sent many minutes or even hours earlier due to the vast distances involved. Engineers on Earth had to anticipate problems and program spacecraft to handle situations autonomously. When things went wrong, creative solutions were devised across millions of miles of space. When things went right, these machines sent back treasures of knowledge that transformed our understanding of the solar system. These robotic missions revealed that our solar system contains a stunning diversity of worlds, each with its own story. They found active geology on moons and dwarf planets, discovered organic molecules on distant bodies, and identified numerous locations where life might exist beyond Earth. They extended human presence to every planet and many smaller worlds, accomplishing exploration that would be impossible for human travelers given current technology. As robotic explorers continued their patient work throughout the solar system, plans were already forming for the next phase of human exploration, building on the decades of experience gained aboard the International Space Station. As our robotic explorers ventured deeper into the solar system, revealing the secrets of distant worlds, humanity was also learning to establish a permanent presence much closer to home. High above Earth's surface, a remarkable structure was taking shape, piece by carefully assembled piece, against the darkness of space. The International Space Station, often simply called the ISS, represents perhaps the most ambitious cooperative project in human history. Construction began in 1998 when a Russian Proton rocket carried the Zarya module into orbit, followed weeks later by the Space Shuttle Endeavour delivering the Unity node. What started as two connected modules would grow over the next 13 years into a sprawling complex the size of a football field, with living space comparable to a 6-bedroom house. The station orbits Earth every 90 minutes at an altitude of approximately 400 kilometers, traveling at a velocity of nearly 28,000 kilometers per hour. Yet inside its pressurized modules, astronauts float peacefully through their daily routines, conducting experiments that can only be performed in the unique environment of microgravity. The soft hum of ventilation fans and the gentle whirring of equipment create a constant background symphony in this orbital laboratory. What makes the International Space Station truly extraordinary is not just its technical achievements, but the spirit of collaboration it embodies. 15 nations contributed to its design and construction, including the United States, Russia, Japan, Canada, and 11 members of the European Space Agency. Crews from more than 20 countries have lived aboard the station, working together despite the political tensions that sometimes divide their governments on Earth below. In the quiet corridors of the ISS, floating through modules with names like Destiny, Columbus, and Kibo, astronauts and cosmonauts have demonstrated that humans can achieve remarkable things when they work toward common goals. The station serves as a laboratory for thousands of experiments. Scientists study how the human body adapts to long periods in space. Knowledge essential for future missions to Mars and beyond. Researchers grow protein crystals that form more perfectly in microgravity than on Earth, potentially leading to better medicines. They observe how flames burn in weightlessness, how fluids behave without the influence of gravity, and how plants grow when there is no up or down. Each experiment conducted in this orbiting laboratory adds another piece to our understanding of the universe and our place within it. Life aboard the International Space Station follows carefully structured routines that help maintain both physical and mental health during stays that typically last 6 months. Astronauts spend several hours each day exercising on specialized equipment to prevent the muscle and bone loss that occurs in weightlessness. They conduct spacewalks to maintain and upgrade the station's systems, floating outside in their spacesuits, while Earth revolves majestically beneath them. They share meals together in the various modules, food packages secured with Velcro to prevent them from drifting away, and they video call their families on Earth during precious personal time. Through the station's windows, known as the cupola, crew members can gaze down at Earth and watch weather patterns swirl across oceans. City lights sparkle in the darkness, and the delicate blue line of the atmosphere that protects all life on our planet. Many astronauts speak of how this view changes their perspective, seeing Earth as one interconnected world without visible borders, a fragile oasis of life in the vast darkness of space. The knowledge gained from decades of space station operations, from the early Soviet Salyut stations through Mir and Skylab to the ISS, has taught us that humans can indeed live and work productively in space for extended periods. This understanding now fuels ambitious plans for humanity's next steps beyond low Earth orbit. Multiple space agencies are developing plans to return humans to the Moon, not just for brief visits as during the Apollo era, but to establish sustained lunar bases. The Artemis program, led by NASA with international partners, aims to land the first woman and the next man on the lunar surface and create a permanent human presence there. A small space station called Gateway will orbit the Moon, serving as a staging point for lunar landings, and eventually as a stepping stone for missions deeper into the solar system. On the lunar surface itself, astronauts may establish research stations where they can learn to use local resources, extracting water from ice deposits in permanently shadowed craters, and developing technologies for living off the land of another world. Mars beckons as humanity's next great destination. Multiple space agencies and private companies are developing plans to send humans to the Red Planet, likely in the coming decades. The journey to Mars will take approximately 6 to 9 months each way, requiring spacecraft far more sophisticated than anything built before. Astronauts will need to be extraordinarily self-sufficient, as communication delays of up to 20 minutes each way make real-time assistance from Earth impossible. The first Mars explorers, will spend many months on the surface before the planets align favorably for a return journey, conducting research, searching for signs of past or present life, and establishing the foundations for future human settlement. The landscape of space exploration has also transformed with the emergence of commercial spaceflight. Private companies now launch cargo to the International Space Station and have begun carrying astronauts as well. Space tourism is becoming a reality, with private individuals experiencing brief flights to the edge of space or orbital journeys aboard commercial spacecraft. These developments promise to make space more accessible, opening opportunities that once existed only for highly trained government astronauts. Small satellites, some no larger than a loaf of bread, are being deployed in growing numbers, democratizing access to space for universities, small companies, and even ambitious students. New telescopes, following in the tradition of Hubble, peer deeper into space and time, observing the first galaxies that formed after the universe's birth, and searching thousands of distant stars for planets that might harbor life. As we rest here tonight, the International Space Station continues its silent orbit overhead, passing across the sky like a moving star for those fortunate enough to spot it. Inside, astronauts from different nations work side by side, conducting research that benefits all humanity. Robotic spacecraft journey through the solar system, sending back images and data from worlds we have only begun to explore. And on Earth, engineers and scientists prepare the next generation of missions that will carry humans farther from home than ever before. The story of space exploration, which began with ancient people gazing up in wonder at the night sky, continues to unfold. From those first careful observations of planetary movements, to rockets breaking free of Earth's gravity, from the first tentative orbital flights to footprints on the Moon, from robotic explorers revealing distant worlds to the permanent human presence aboard the International Space Station, each chapter builds upon the last. The adventure is far from over. It is simply entering its next phase as humanity prepares to become a truly spacefaring species, venturing outward to explore the cosmic ocean that surrounds our small blue world. As we bring to a close our journey through humanity's timeless quest to explore the cosmos, from ancient stargazers to modern astronauts venturing beyond our world, we hope these stories have gently carried you through the evening. Thank you for joining us on this peaceful exploration among the stars. If these calm adventures have brought you comfort, we'd love to have you with us again. Like, subscribe, and share your thoughts in the comments below. And now, as the night deepens and your mind settles, let the vastness of space remind you of the infinite possibilities that await in your dreams. Good night, fellow dreamer, and may your sleep be restful and your dreams be kind.